we're kind of in the vacuum tube days of quantum computing. What are your thoughts in this wholly different kind of space of architectures?
I actually, quantum computing idea has been around for a while, and I actually thought, well, I sure hope I retire before I have to start teaching this. I'd say because I give these talks about the slowing of Moore's law, and when we need to change by doing domain-specific accelerators, a common question is, say, what about quantum computing? The reason that comes up, it's in the news all the time. So I think the hard thing to keep in mind is quantum computing is not right around the corner. There have been two national reports, one by the National Academies of Engineering, another by the Computing Consortium, where they did a frank assessment of quantum computing. And both of those reports said, as far as we can tell, before you get error-corrected quantum computing, it's a decade away. So I think of it like nuclear fusion, right? There have been people who've been excited about nuclear fusion a long time. If we ever get nuclear fusion, it's going to be fantastic for the world. I'm glad people are working on it, but it's not right around the corner. Those two reports to me say probably it'll be 2030 before quantum computing is something that could happen. And when it does happen, this is going to be big science stuff. This is, micro Kelvin, almost absolute zero things that if they vibrate, if truck goes by, it won't work, right? So this will be in data center stuff. We're not going to have a quantum cell phone. And it's probably a 2030 kind of thing. So I'm happy that other people are working on it, but just, it's hard with all the news about it not to think that it's right around the corner. And that's why we need to do something as Moore's law is slowing down to provide the computing, keep computing getting better for this next decade. And we shouldn't be betting on quantum computing, or expecting quantum computing to deliver in the next few years. It's probably further off. I'd be happy to be wrong. It'd be great if quantum computing is going to be commercially viable, but it will be a set of applications. It's not a general purpose computation. So it's going to do some amazing things, but there'll be a lot of things that probably, the old-fashioned computers are going to keep doing better for quite a while.
And there'll be a teenager 50 years from now watching this video saying, look how silly David Patterson was, saying...
No, I said 2030. Okay. I didn't say never.
We're not going to have quantum cell phones, so he's going to be watching it on a quantum cell phone.
I think this is such a, given that we've had Moore's law, I feel comfortable trying to do projects that are thinking about the next decade. I admire people who are trying to do things that are 30 years out, but it's such a fast-moving field. I just don't know how to... I'm not good enough to figure out what's the problem's going to be in 30 years. 10 years is hard enough for me.
So you mentioned simulation. This is super interesting to me, and this perhaps could be a super dumb question, but
no such thing.
I'm going to prove you wrong on that one. You simulate molecules to understand how they look from a distance, is what I understand. Like, what does that simulation look like? So it's talking about the which colors of the rainbow will be missing. Is that the goal of the simulation?
That's the goal, but it's really just a very, very nasty Schrodinger's equation. So it's a quantum simulation.
Oh, so it's simulating at the quantum level.
Yes. So I'm a quantum astrochemist. Hi, I'm Clara. I'm a quantum astrochemist. That's how we should have started this conversation.
Can you describe the three components of that quantum astro and chemist and how they interplay together?
So I study the quantum behavior of molecules, hence the quantum and the chemist, specifically so I can detect them in space, hence the astro. So what I do is I figure out the probability of a molecule being in a particular state. There's no deterministic nature to the work I do. So it's every transition is just a likelihood. But if you get a population of that molecule, it will always happen. And so this is all at the quantum level. It's a Schrödinger equation on, I think, 27 dimensions. I don't remember it by heart. And what this means is I'm solving these giant quantum matrices. And that's why you need a lot of computer power, giant computers, to diagonalize these enormous matrices, each of whom describes a single vibrational behavior of a molecule. So I think phosphine has 17.5 million possible states it can exist in. And transitions can occur between pairs of these states. And there's a certain likelihood that they'll happen. This is the quantum world. Nothing is deterministic. There's just a likelihood that it will jump from one state to another. And these jumps, they're transitions. And there's 16.8 billion of them. When energy is absorbed, that corresponds to this transition. We see it in the spectrum. This is more quantum chemistry than you had asked for. I'm sorry.
No, I'm sorry. Brain's broken. So when the transitions happen between the different states, somehow the energy maps to the spectrum.
Exactly. Energy corresponds to a frequency, and a frequency corresponds to a wavelength, which corresponds to a color.
So there's some probability assigned to each color then?
Exactly. And that probability determines how intense that transition will be, how strong.
And so you run this kind of simulation for particular, so that's 17.5 squared or something like that.
Exactly. 17.5 million energies, each one of whom involves diagonalizing a giant matrix with a supercomputer.
Actually, I wonder what the most efficient algorithm for diagonalization is. But there's some kind of...
There's many.
There's many, yeah.
It depends on kind of the shape of the matrix. So they're not random matrices. So some are more diagonal than others. And so some need more treatment than others. Most of the work ends up going in describing this system, this quantum system, in different ways until you have a matrix that is close to being diagonal. And then it's much easier to clean it up.
So how hard is this puzzle? So you're solving this puzzle for phosphine, right? Are we supposed to solve this puzzle for every single molecule? Oh boy.
Yes, I calculated if I did the work I did for phosphine, again, for all the molecules for which we don't have spectra, for which we don't have a fingerprint, it would take me 62,000 years, a little over.
62,000 years. Well, time flies when you're having fun. Okay, but you write that there are about 16,000 molecules we care about when looking for a new Earth or when we try to detect alien biosignatures. If we want to detect any molecules from here, we need to know their spectra, and we currently don't. Solving this particular problem, that's my job.
Where was that? That's absolutely correct.
Yeah.
I could have not said it better myself. Did you take that from my website?
Yeah, I think I stole it. And your website is excellent, so it's a worthy place to steal stuff from.
Thank you.
How do you solve this problem for the 16,000 molecules we care about, of which phosphine is one?
Yes.
And so, so taking a step a little bit out of phosphine, is there...
But we were having so much fun.
We were having so much fun. No, we're not saying
No,
it's sticking around. I'm just saying we're joining more friends coming to the party. How do you choose other friends to come to the party that are interesting to study as we solve one puzzle at a time through the space of 16,000?
So we've already started. Out of those 16,000, we understand water quite well, methane quite well, ammonia quite well, carbon dioxide. I could keep going. And then we understand molecules like acetylene, hydrogen cyanide, more or less. And that takes us to about 4% of those 16,000. We understand about 4% of them, more or less. Phosphine is one of them. But the other 96%, we just really have barely any idea at all of where in the spectrum of light they would leave a mark. I can't spend the next 62,000 years doing this work, and I don't want to. Even if somehow I was able, that wouldn't feel good. So one of the things that I try to do now is move away from how I did phosphine. So I did phosphine really the best that could be done with the computer power that we have. Trying to get each one of those 16.8 billion transitions mapped, accurately calculated. And then I thought, what if I do a worse job? What if I just do a much worse job? Can I just make it much faster and then it's still worth it?
Yes.
Like, how bad can I get before it's worthless? And then could I do this for all the other molecules?
Yes.
So I created exactly this terrible, terrible
So
system.
what's the answer to that question, that fundamental question I ask myself all the time in other domains?
How crappy can I be before I'm useless?
Before somebody notices.
Turns out pretty crappy, because
Excellent.
no one has any idea what these molecules look like. Anything is better than nothing. And so I thought, how long will it take me to create better than nothing spectra for all of these molecules? And so I created RASCAL, Rapid Approximate Spectral Calculations for All. And what I do is I use organic chemistry and quantum chemistry and kind of cheat at them both. I just try to figure out what is the fastest way I could run this. And I simulate rough spectra for all of those 16,000. So I've managed to get it to work. It's really shocking how well it works, considering how bad it is.
Is there insights you could give to like the tricks involved in making it fast? Like what are the maybe some insightful shortcuts taken that still result in some useful information about the spectra?
The insights came from organic chemistry from decades ago. When organic chemists wanted to know what a compound might be, they would look at a spectrum and see a feature, and they would go, I've seen that feature before. That's usually what happens when you have a carbon triple bonded to another carbon. And they were mostly right. Almost every molecule that has a carbon triple bonded to another one looks like that. Has other features different that distinguish them from one another, but they have that feature in common. We call these functional groups. And so most of that work ended up being abandoned because now we have mass spectrometry, we got nuclear magnetic resonance spectroscopy, so people don't really need to do that anymore. But these ancient textbooks still exist, and I've collected them all, as many as I could. And there are hundreds of these descriptions where people have said, oh, whenever you have a iodine atom connected to this one, there's always a feature here, and it's usually quite sharp and it's quite strong. And some people go, oh yeah, that's a really broad feature every time that combination of atoms and bonds. So I've collected them all, and I've created this giant dictionary of all these kind of puzzle pieces, these Lego parts of molecules. And I've written a code that then puts them all together in some kind of like Frankenstein's monster of molecules. So you ask me for any molecule, and I go, well, it has these bonds and this atom dangling off this atom and this cluster here. And I tell you what it should look like. And it kind of works.
So this creates a whole portfolio of just kind of signatures that we could look for.
Very rough signatures.
But still useful enough to analyze the atmospheres, the telescope-generated images of other planets.
Close. Right now, it is so complete. So it has all of these molecules that it can tell you, say you look at an alien atmosphere and there's a feature there. It can tell you, oh, that feature, that's familiar. It could be one of these 816 molecules. Best of luck.
Yes.
So I think the next step, which is what I'm working on, is telling you something more useful than it could be one of those 816 molecules. That's still true. I wouldn't say it's useful. So I can tell you, but only 12% of them also have a feature in this region, so go look there. And if there's nothing there, it can't be those, and so on. It can also tell you things like, you will need this much accuracy to distinguish between those 816. So that's what I'm working on, but it's a lot of work.
So this is really interesting, the role of computing in this whole picture. You mentioned code. So like you as a quantum astrochemist, there is some role for programming in your life, in your past life, in your current life?
Oh yeah, almost entirely. I'm a computational quantum astrochemist, but that doesn't roll off the tongue very easily.
So this is fundamentally computational. Like if you want to be successful in the 21st century in doing quantum astrochemistry, you want to be computational?
Absolutely. All quantum chemistry is computational at this point.
Okay. What does machine learning play a role at all? Is there some extra shortcuts that could be discovered through, like you see all that success with protein folding, right? A problem that thought to be extremely difficult to apply machine learning to because it's, mostly because there's not a lot of already solved puzzles to train on. I suppose the same exact thing is true with this particular problem, but is there hope for machine learning to help out?
Absolutely. Currently, you've laid out exactly the problem. The training set is awful. And because a lot of this data that I'm basing it on is literally many decades old. The people who worked on it and data that I get, often they're dead. And the files that I've used, some of them were hand-drawn by someone tired in the 70s.
Yes.
So I can, of course, have a program training on these, but I would just be perpetuating these mistakes without hope of actually verifying them. So my next step is to improve this training set by hand, and then try to see if I can apply machine learning on the full code of the full 16,000 molecules and improve them all. But really, I need to be able to test the outcomes with experimental data, which means convincing someone in a lab to spend a lot of money putting very dangerous gases in chambers and measuring them at outrageous temperatures. So it's a work in progress.
And so collecting huge amounts of data about the actual gases. So you are up for doing that kind of thing too? So actually, like, doing the full end-to-end thing, which is like having a gas, collecting data about it, and then doing the kind of analysis that creates the fingerprint, and then also analyzing using that library the data that comes from other planets. So you do the full
from birth to death.
Interesting.
Yes, I worked in an industrial chemistry laboratory when I was much younger in Slovenia. And there I worked in the lab actually collecting spectra and predicting spectra.
What's it like to work with a bunch of gases that are like not so human friendly? Is
terrifying. It's horrific. It's so scary. And I love my job. I'm willing to clearly sacrifice a lot for it. You know, job, stability, money, sanity. But I only worked there for a few months. It was really terrifying. There's just so many ways to die. You know, usually you only have a handful of ways to die every day. You know, but if you work in a lab, there's so many more, like orders of magnitude more. And I was very bad at it. I'm not a good hands-on scientist. I want a laptop connected to a remote supercomputer or a laptop connected to a telescope.
Yes.
I don't need to be there to believe it. And I am not good in the lab.
Yeah, when there's a bunch of things that can poison you, a bunch of things that could explode, and they're gaseous, and they're often... maybe they might not even have a smell, or they might not be visible. It's like...
so many of them give you cancer. It's just so cruel. And some people love this work, but I've never enjoyed experimental work. It's so ungrateful. It's so lonely.
Well, so much work is lonely if you find the joy in it. But you enjoy the results of it.
Yes. I'm very thankful for all the experimentalists in my life. But I'll do the theory, they do the experiment, and then we talk to one another and make sure it matches, you know?
Okay. Do you have a hope that we solve that theory of everything puzzle in the next few decades? So there's been a bunch of attempts from string theory to all kinds of attempts at trying to solve quantum gravity, or basically come up with a theory for quantum gravity. There's a lot of complexities to this. One, for experimental validation, you have to observe effects that are very difficult to measure. So you have to build, that's like an engineering challenge. And then there's the theory challenge, which is like, it seems very difficult to connect the laws of gravity to quantum mechanics. Do you have a hope, or are we hopelessly stuck?
Well, I have to have a hope. I mean, it's in some sense what I devote at least part of my professional life toward trying to make progress on. I'm glad you used the phrase quantum gravity. I'm not a great fan of the theory of everything phrase, because it does make other scientists feel like if they're not working on this, what are they working on? Man, it's like, there's not much left when you're talking about theory of everything.
Biology is just small details.
Yeah, right,
we'll
exactly.
Figure out.
Yeah. So it is really trying to put gravity and quantum mechanics together. And since I was a college kid, I was deeply fascinated with gravity. And as I learned quantum mechanics, the notion of physicists being stumped on trying to blend them together, how could one not get fired up about maybe contributing something to that journey? And so we've been on this, I've been on this for 30 years since I was a student. We have made progress. We do have ideas. You mentioned string theory is one possible scenario. It's not stuck. String theory is a vibrant field of research that is making incredible progress, but we've not made progress on this issue of experimental verification, validation, which is, it is a vital part of the story. So I would have hoped that by now we would have made contact with observation. If you would have interviewed me back in the 80s when I was, a wild, bright-eyed kid trying to make headway, working 18 hours a day and this sort of stuff, I would have said, yeah, by 2021, yeah, we're going to know whether it's right or wrong. We'll have made contact. I would have said, look, there may be certain mathematical puzzles that we've yet to work out, but we'll know enough to make contact with experiment. That has not happened. On the other hand, if you would have interviewed me back then and asked me, will we be able to talk about detailed qualities of black holes and understand them at the level of detail that we actually, I would have said, no, I don't think that we're going to be able to do that. Will we have an exact formulation of string theory in certain circumstances? No, I don't think we're going to have that, and yet we do. So it's just to say you don't know where the progress is going to happen. But yes, I do hold out hope that maybe before I move on to wherever, I don't think there is an after, but I would love before I leave this earth to know the answer. But, science and the universe, it's not about pleasing any individual. It is what it is. And so we just press onward and we'll see.
So if noise is currently like the biggest problem for quantum computing, and then the dream is error correcting quantum computers, can you just maybe describe what does it mean for there to be noise in the system?
Absolutely. So the problem is even a little more specific than noise. So the fundamental problem, if you're trying to actually build a quantum computer, of any appreciable size, is something called decoherence. Okay, and this was recognized from the very beginning, when people first started thinking about this in the 1990s. Now, what decoherence means is sort of unwanted interaction between, your qubits, the state of your quantum computer and the external environment. Okay, and why is that such a problem? Well, I talked before about how, when you measure a quantum system. So let's say if I measure a qubit that's in a superposition of 0 and 1 states to ask it, are you 0 or are you 1? Well, now I force it to make up its mind, right? And now probabilistically it chooses one or the other. And now, it's no longer a superposition. There's no longer amplitudes. There's some probability that I get a 0 and there's some that I get a 1. And now the trouble is that it doesn't have to be me who's looking. Okay, or in fact, it doesn't have to be any conscious entity. Any kind of interaction with the external world that leaks out the information about whether this qubit was a 0 or a 1, sort of that causes the zeroness or the oneness of the qubit to be recorded in, the radiation in the room, in the molecules of the air, in the wires that are connected to my device, any of that. As soon as the information leaks out, it is as if that qubit has been measured. Okay, it is, the state has now collapsed. Another way to say it is that it's become entangled with its environment. Okay, but from the perspective of someone who's just looking at this qubit, it is as though it has lost its quantum state. And so what this means is that if I want to do a quantum computation, I have to keep the qubits sort of fanatically well isolated from their environment. But then at the same time, they can't be perfectly isolated because I need to tell them what to do. I need to make them interact with each other, for one thing. And not only that, but in a precisely choreographed way. Okay. And, that is such a staggering problem, right? How do I isolate these qubits from the whole universe, but then also tell them exactly what to do? I mean, there were distinguished physicists and computer scientists in the 90s who said this is fundamentally impossible. The laws of physics will just never let you control qubits to the degree of accuracy that you're talking about. Now, what changed the views of most of us was a profound discovery in the mid to late 90s, which was called the theory of quantum error correction and quantum fault tolerance. Okay, and the upshot of that theory is that if I want to build a reliable quantum computer and scale it up to, an arbitrary number of as many qubits as I want, and doing as much on them as I want, I do not actually have to get the qubits perfectly isolated from their environment. It is enough to get them really, really, really well isolated. Okay. And even if every qubit is sort of leaking, its state into the environment at some rate, as long as that rate is low enough, okay, I can sort of encode the information that I care about in very clever ways across the collective states of multiple qubits. Okay, in such a way that even if a small percentage of my qubits leak, well, I'm constantly monitoring them to see if that leak happened. I can detect it and I can correct it. I can recover the information I care about from the remaining qubits. Okay, and so you can build a reliable quantum computer even out of unreliable parts. Right now, in some sense, that discovery is what set the engineering agenda for quantum computing research from the 1990s until the present. Okay, the goal has been, engineer qubits that are not perfectly reliable, but reliable enough that you can then use these error correcting codes to have them simulate qubits that are even more reliable than they are, right?
Got
So
it.
the error correction becomes a net win rather than a net loss, right? And then once you reach that sort of crossover point, then, your simulated qubits could in turn simulate qubits that are even more reliable and so on until you've just, effectively you have arbitrarily reliable qubits. So long story short, we are not at that break-even point yet. We're a hell of a lot closer than we were when people started doing this in the 90s, like orders of magnitude closer.
But the key ingredient there is the more qubits, the better. Because
well, the more qubits, the larger the computation you can do, right? Qubits are what constitute the memory of your quantum computer, right?
but also for the for the error correcting mechanism.
Yes. So the way I would say it is that error correction imposes an overhead in the number of qubits, and that is actually one of the biggest practical problems with building a scalable quantum computer. If you look at the error correcting codes, at least the ones that we know about today, and you look at, what would it take to actually use a quantum computer to, hack your credit card number, which is, maybe, the most famous application people talk about, right? Let's say to factor huge numbers and thereby break the RSA crypto system. Well, what that would take would be several thousand logical qubits. But now with the known error correcting codes, each of those logical qubits would need to be encoded itself using thousands of physical qubits. So at that point, you're talking about millions of physical qubits. And in some sense, that is the reason why quantum computers are not breaking cryptography already. It's because of these immense overheads involved.
So that overhead is additive or multiplicative?
Well, it's multiplicative. I mean, it's like you take the number of logical qubits that you need in your abstract quantum circuit, you multiply it by 1,000 or so. So, there's a lot of work on, trying to invent better error correcting codes. Okay, but that is the situation right now. In the meantime, we are now in what the physicist John Preskill called the noisy intermediate scale quantum, or NISQ era. And this is the era, you can think of it as sort of like the vacuum, we're now entering the very early vacuum tube era of quantum computers. The quantum computer analog of the transistor has not been invented yet. Right, that would be like true error correction, right? Where we are not, or something else that would achieve the same effect, right? We are not there yet, but where we are now, let's say as of a few months ago, as of Google's announcement of quantum supremacy, we are now finally at the point where even with a non-error corrected quantum computer, with these noisy devices, we can do something that is hard for classical computers to simulate. Okay, so we can eke out some advantage. Now, will we in this noisy era be able to do something beyond what a classical computer can do that is also useful? to someone. That we still don't know. People are going to be racing over the next decade to try to do that. By people, I mean Google, IBM, a bunch of startup companies,
and research
players
labs.
and research labs and governments and
Google announced with their work in the paper in Nature with quantum supremacy.
Yes.
Can you describe, again, back to the basic, what is, perhaps not so basic, what is quantum supremacy?
Absolutely. So quantum supremacy is a term that was coined by John Preskill in 2012. Not everyone likes the name, but it sort of stuck. We don't. We sort of haven't found a better alternative.
It's technically quantum computational supremacy.
Supremacy. That's right. And but the basic idea is actually one that goes all the way back to the beginnings of quantum computing, when Richard Feynman and David Deutsch, people like that, were talking about it in the early '80s. And quantum supremacy just refers to sort of the point in history when you can first use a quantum computer to do some well-defined task much faster than any known algorithm running on any of the classical computers that are available. Okay, so notice that I did not say a useful task.
Yes.
Okay, it could be something completely artificial, but it's important that the task be well defined. So in other words, it is something that has right and wrong answers, and that are knowable independently of this device, right? And we can then, run the device, see if it gets the right answer or not.
Can you clarify a small point? You said much faster than a classical implementation. Yeah. What about the space where the class it doesn't even exist a classical algorithm
So maybe I should clarify. Everything that a quantum computer can do, a classical computer can also eventually do. Okay, and the reason why we know that is that a classical computer could always, if it had no limits of time and memory, it could always just store the entire quantum state, of your, of the quantum, or store a list of all the amplitudes, in the state of the quantum computer, and then just, do some linear algebra to just update that state, right? And so anything that quantum computers can do can also be done by classical computers, albeit exponentially slower.
So quantum computers don't go into some magical place outside of Alan Turing's definition of computation.
Precisely. They do not solve the halting problem.
Right.
They cannot solve anything that is uncomputable in Alan Turing's sense. What we think they do change is what is efficiently computable. Okay, and since the 1960s, the word efficiently, has been a central word in computer science, but it's sort of a code word for something technical, which is basically with polynomial scaling. That as you get to larger and larger inputs, you would like an algorithm that uses an amount of time that scales only like the size of the input raised to some power, and not exponentially with the size of the input, right?
So I do hope we get to talk again, because one of the many topics that there's probably several hours worth of conversation on is complexity, which we probably won't even get a chance to touch today. But you briefly mentioned it. But let's maybe try to continue. So you said the definition of quantum supremacy is basically is achieving a place where much faster on a formal, that quantum computer is much faster on a formal, well-defined problem.
Yes,
that is or isn't useful.
Right. And I would say that we really want three things, right? We want, first of all, the quantum computer to be much faster, just in the literal sense of like number of seconds, just solving this, well-defined, problem. Secondly, we want it to be sort of, for a problem where we really believe that a quantum computer has better scaling behavior, right? So it's not just an incidental, matter of hardware, but it's that, as you went to larger and larger inputs, the classical scaling would be exponential, and the scaling for the quantum algorithm would only be polynomial. And then thirdly, we want the first thing, the actual observed speed up, to only be explainable in terms of the scaling behavior, right? So, I want a real world, a real problem to get solved let's say by a quantum computer with 50 qubits or so, and for no one to be able to explain that in any way other than, well, this computer involved a quantum state with 2 to the 50th power amplitudes. And, a classical simulation, at least any that we know today, would require keeping track of 2 to the 50th numbers. And this is the reason why it was faster.
So the intuition is that then if you demonstrate on 50 qubits, then once you get to 100 qubits, then it'll be even much more faster.
Precisely. Yeah, and quantum supremacy does not require error correction, right? We don't have, you could say, true scalability yet, or true, error correction yet. But you could say quantum supremacy is already enough by itself to refute the skeptics who said a quantum computer will never outperform a classical computer for anything.
But one, how do you demonstrate quantum supremacy? And two, what's up with these new news articles I'm reading that Google did so?
Yeah. All right. Well,
what did they actually do?
Great questions, because now you get into actually, a lot of the work that I and my students have been doing for the last decade, which was precisely about how do you demonstrate quantum supremacy using technologies that, we thought would be available in the near future. And so one of the main things that we realized around 2011, and this was me and my student, Alex Arkhipov at MIT at the time, and independently, some others, including Bremner, Joza, and Shepard. Okay, and the realization that we came to was that if you just want to prove that a quantum computer is faster, and not do something useful with it, then there are huge advantages to sort of switching your attention from problems like factoring numbers that have a single right answer to what we call sampling problems. So these are problems where the goal is just to output a sample from some probability distribution, let's say over strings of 50 bits, right? So there are, many, many, many possible valid outputs. Your computer will probably never even produce the same output twice, if it's running as even, assuming it's running perfectly. Okay. But the key is that some outputs are supposed to be likelier than other ones. So
sorry, to clarify, is there a set of outputs that are valid and set that are not? Or is it more that the distribution of a particular kind of output is like there's a specific distribution of a particular kind of output?
There's a specific distribution that you're trying to hit, right? Or that you're trying to sample from. Now there are a lot of questions about this. How do you do that? Right? Now how you do it, it turns out that with a quantum computer, even with the noisy quantum computers that we have now, that we have today, what you can do is basically just apply a randomly chosen sequence of operations, right? So we in some of that part is almost trivial, right? We just sort of get the qubits to interact in some random way, although a sort of precisely specified random way, so we can repeat the exact same random sequence of interactions again and get another sample from that same distribution. And what this does is it basically, it creates a lot of garbage, but, very specific garbage, right? So, of all of the, so if we're going to talk about Google's device, there were 53 qubits there, okay? And so there are 2 to the 53 power possible outputs. Now, for some of those outputs, there was a little bit more destructive interference in their amplitude. Okay, so their amplitudes were a little bit smaller. And for others, there was a little more constructive interference. The amplitudes were a little bit more aligned with each other. And so those were a little bit likelier. Okay, all of the outputs are exponentially unlikely, but some are, let's say, 2 times or 3 times, unlikelier than others. Okay, right. And so you can define, this sequence of operations that gives rise to this probability distribution. Okay, now the next question would be, well, how do you, even if you're sampling from it, how do you verify that?
Right.
How do you know? And so my students and I, and also the people at Google who were doing the experiment, came up with statistical tests that you can apply to the outputs in order to try to verify, what is, that at least that some hard problem is being solved. The test that Google ended up using was something that they called the linear cross entropy benchmark. Okay, and it's basically, so the drawback of this test is that it requires you to do a 2 to the 53 time calculation with your classical computer. Okay, so it's very expensive to do the test on a classical computer. The good news
How
is
big of a number is 2 to the 50?
it's about 9 quadrillion. Okay,
That doesn't help.
Well, it's you want it in like scientific notation.
No. What I mean is,
it is
impossible to run on a
So we will come back to that. It is just barely possible to run, we think, on the largest supercomputer that currently exists on Earth, which is called Summit at Oak Ridge National Lab. Okay.
Great. This is exciting.
That's the short answer. So ironically, for this type of experiment, we don't want 100 qubits. Okay, because with 100 qubits, even if it works, we don't know how to verify the results. Okay, so we want, a number of qubits that is enough that, the biggest classical computers on Earth will have to sweat, and will just barely, be able to keep up with the quantum computer, using much more time, but they will still be able to do it in order that we can verify the results.
Which is where the 53 comes from for the
basically.
Number of
well,
qubits.
I mean, that's also that's sort of that's sort of where they are now in terms of scaling, and then soon that point will be passed, and then when you get to larger numbers of qubits, then these types of sampling experiments will no longer be so interesting because we won't even be able to verify the results, and we'll have to switch to other types of computation. So with the sampling thing, so the test that Google applied with this linear cross entropy benchmark was basically just take the samples that were generated, which are, a very small subset of all the possible samples that there are. But for those, you calculate with your classical computer the probabilities that they should have been output. And you see, are those probabilities like larger than the mean? So is the quantum computer biased toward outputting the strings that it's, that you want it to be biased toward? Okay. And then finally, we come to a very crucial question, which is supposing that it does that. Well, how do we know that a classical computer could not have quickly done the same thing? Right? How do we know that, this couldn't have been spoofed by a classical computer? Right. And so, the first answer is we don't know for sure. Because this takes us into questions of complexity theory, right. Questions of the magnitude of the P versus NP question and things like that, right? We don't know how to rule out definitively that there could be fast classical algorithms for even simulating quantum mechanics and for simulating experiments like these, but we can give some evidence against that possibility. And that was sort of the main thrust of a lot of the work that my colleagues and I did, over the last decade, which is then sort of in around 2015 or so, what led to Google deciding to do this experiment.
So is the kind of evidence here, first of all, the hard P equals NP problem that you mentioned, and the kind of evidence that you're were looking at, is that something you come to on a sheet of paper? Or is this something? Are these empirical experiments?
It's math for the most part. I mean, it's also we have a bunch of methods that are known for simulating quantum circuits or quantum computations with classical computers, and so we have to try them all out and make sure that they don't work. Right. Make sure that they have exponential scaling on these problems, and not just theoretically, but with the actual range of parameters that are actually arising in Google's experiment. Okay, so there is an empirical component to it, right? But now on the theoretical side, what we know how to do in theoretical computer science and computational complexity is, we don't know how to prove that most of the problems we care about are hard. but we know how to pass the blame to someone else. Okay, we know how to say, well, look, I can't prove that this problem is hard, but if it is easy, then all these other things that you probably were much more confident or were hard, then those would be easy as well. Okay, so we can give what are called reductions. And this has been the basic strategy in NP completeness, right? In all of theoretical computer science and cryptography since the 1970s, really. And so we were able to give some reduction evidence for the hardness of simulating these sampling experiments, these sampling-based quantum supremacy experiments. The reduction evidence is not as satisfactory as it should be. One of the biggest open problems in this area is to make it better. But, we can do something. Certainly we can say that, if there is a fast classical algorithm to spoof these experiments, then it has to be very, very unlike any of the algorithms that we know.
Which is kind of in the same kind of space of reasoning that people say P not equals NP.
Yeah, it's in the same spirit.
Yeah, in the same spirit. Okay, so as you've said, quantum computing, at least in the 1990s, was a profound story at the intersection of computer science, physics, engineering, math, and philosophy. So there's this broad and deep aspect to quantum computing that represents more than just the quantum computer.
Yes.
But can we start at the very basics? What is quantum computing?
Yeah. So it's a proposal for a new type of computation, or let's say a new way to harness nature to do computation that is based on the principles of quantum mechanics. Okay, now the principles of quantum mechanics have been in place since 1926. They haven't changed. What's new is, how we want to use them. Okay, so what does quantum mechanics say about the world? The physicists, I think, over the generations, convinced people that is an unbelievably complicated question, and just give up on trying to understand it. I can let you in, not being a physicist, I can let you in on a secret, which is that it becomes a lot simpler if you do what we do in quantum information theory and sort of take the physics out of it. So the way that we think about quantum mechanics is sort of as a generalization of the rules of probability themselves. So, you might say there was a 30% chance that it was going to snow today or something. You would never say that there was a negative 30% chance, right? That would be nonsense. Much less would you say that there was an I% chance, a square root of minus 1% chance. Now, the central discovery that sort of quantum mechanics made is that fundamentally the world is described by the sort of, let's say, the possibilities for what a system could be doing are described using numbers called amplitudes, okay, which are like probabilities in some ways, but they are not probabilities. They can be positive. For one thing, they can be positive or negative. In fact, they can even be complex numbers. Okay, and if you've heard of a quantum superposition, this just means some state of affairs where you assign an amplitude, one of these complex numbers, to every possible configuration that you could see a system in on measuring it. So, for example, you might say that an electron has some amplitude for being here and some other amplitude for being there, right? Now, if you look to see where it is, you will localize it, right? You will sort of force the amplitudes to be converted into probabilities. That happens by taking their squared absolute value, okay? And then you can say either the electron will be here or it will be there. And knowing the amplitudes, you can predict at least the probabilities that you'll see each possible outcome. Okay, but while a system is isolated from the whole rest of the universe, the rest of its environment, the amplitudes can change in time by rules that are different from the normal rules of probability, and that are alien to our everyday experience. So anytime anyone ever tells you anything about the weirdness of the quantum world, or assuming that they're not lying to you, right? They are telling you, yet another consequence of nature being described by these amplitudes. So most famously, what amplitudes can do is that they can interfere with each other. Okay, so in the famous double slit experiment, what happens is that you shoot a particle, like an electron, let's say, at a screen with two slits in it, and you find that there are, on a second screen, now there are certain places where that electron will never end up, after it passes through the first screen. And yet, if I close off one of the slits, then the electron can appear in that place. Okay. Mm-hmm. So by decreasing the number of paths that the electron could take to get somewhere, you can increase the chance that it gets there. Okay. Now, how is that possible? Well, it's because as we would say now, the electron has a superposition state. Okay. It has some amplitude for reaching this point by going through the first slit. It has some other amplitude for reaching it by going through the second slit. But now if one amplitude is positive and the other one is negative, then I have to add them all up, right? I have to add the amplitudes for every path that the electron could have taken to reach this point. And those amplitudes, if they're pointing in different directions, they can cancel each other out. And that would mean the total amplitude is 0 and the thing never happens at all. I close off one of the possibilities, then the amplitude is positive or it's negative, and now the thing can happen. Okay, so that is sort of the one trick of quantum mechanics. And now I can tell you what a quantum computer is. Okay, a quantum computer is a computer that tries to exploit these phenomena, superposition, amplitudes, and interference, in order to solve certain problems much faster than we know how to solve them otherwise. So the basic building block of a quantum computer is what we call a quantum bit or a qubit. That just means a bit that has some amplitude for being 0 and some other amplitude for being 1. So it's a superposition of 0 and 1 states, right? But now the key point is that if I've got, let's say, 1,000 qubits, the rules of quantum mechanics are completely unequivocal that I do not just need I don't just need amplitudes for each qubit separately. Okay, in general, I need an amplitude for every possible setting of all 1,000 of those bits. Okay, so that what that means is 2 to the 1,000 power amplitudes. Okay, if I had to write those down, let's say in the memory of a conventional computer, if I had to write down 2 to the 1,000 complex numbers, that would not fit within the entire observable universe. Okay, and yet, quantum mechanics is unequivocal that if these qubits can all interact with each other, and in some sense, I need 2 to the 1,000 parameters, amplitudes to describe what is going on. Now, now I can tell where all the popular articles, about quantum computing go off the rails is that they say, they sort of say what I just said, and then they say, oh, so the way a quantum computer works is just by trying every possible answer in parallel.
Right.
That sounds too good to be true, and unfortunately, it kind of is too good to be true. The problem is, I could make a superposition over every possible answer to my problem, even if there were 2 to the 1,000 of them. Right? I can easily do that. The trouble is, for a computer to be useful, at some point you've got to look at it and see an output. Right? And if I just measure a superposition over every possible answer, then the rules of quantum mechanics tell me that all I'll see will be a random answer. If I just wanted a random answer, well, I could have picked one myself with a lot less trouble, right? Yeah. So the entire trick with quantum computing, with every algorithm for a quantum computer, is that you try to choreograph a pattern of interference of amplitudes. And you try to do it so that for each wrong answer, some of the paths leading to that wrong answer have positive amplitudes and others have negative amplitudes. So on the whole, they cancel each other out. Okay, whereas all the paths leading to the right answer should reinforce each other, should have amplitudes pointing the same direction.
So the design of algorithms in the space is the choreography of the interferences.
Precisely. That's precisely what it is.
Can we take a brief step back and
Sure.
You mentioned information.
Yes.
So in which part of this beautiful picture that you've painted is information contained?
Oh, well, information is at the core of everything that we've been talking about, right? I mean, the bit is, the basic unit of information since, Claude Shannon's paper in 1948. And of course, people had the concept even before that. He popularized the name, right? But I mean,
But a bit is 0 or 1.
That's
so that's
right.
a basic element
that's
of
right. And
information.
what we would say is that the basic unit of quantum information is the qubit, is, the object, any object that can be maintained in manipulated in a superposition of 0 and 1 states. Now, sometimes people ask, well, but what is a qubit physically, right? And there are all these different, proposals that are being pursued in parallel for how you implement qubits. There is, superconducting quantum computing that was in the news recently because of Google's quantum supremacy experiment, right? Where you would have some little coils where a current can flow through them in two different energy states, one representing a 0, another representing a 1. And if you cool these coils to just slightly above absolute 0, like 100th of a degree, then they superconduct. And then the current can actually be in a superposition of the two different states. So that's one kind of qubit. Another kind would be, just an individual atomic nucleus, right? It has a spin. It could be spinning clockwise, it could be spinning counterclockwise, or it could be in a superposition of the two spin states. That is another qubit. But see, just like in the classical world, right, you could be a virtuoso programmer without having any idea of what a transistor is, right, or how the bits are physically represented inside the machine, or even that the machine uses electricity, right? You just care about the logic. It's sort of the same with quantum computing, right? Qubits could be realized by many, many different quantum systems, and yet all of those systems will lead to the same logic, the logic of qubits and how you measure them, how you change them over time. And so the subject of how qubits behave and what you can do with qubits, that is quantum information.
So just to linger on that,
Sure.
So the physical design implementation of a qubit does not interfere with that next level of abstraction that you can program over it. So it truly is, the idea of it is okay.
Well, to be honest with you, today they do interfere with each other. That's because all the quantum computers we can build today are very noisy, right? And so sort of the qubits are very far from perfect, and so the lower level sort of does affect the higher levels, and we sort of have to think about all of them at once. Okay, but eventually, where we hope to get is to what are called error-corrected quantum computers, where the qubits really do behave like perfect abstract qubits for as long as we want them to. And in that future, a future that we can already sort of prove theorems about or think about today, but in that future, the logic of it really does become decoupled from the hardware down.
So you're one of the world-class researchers in this space. There's a few groups, like we mentioned, Google and IBM working at this. There's other research labs, but you put also you have an amazing blog. You put
You're
a
too
lot.
Kind.
You put a you paid me to say it. You put a lot of effort sort of to communicating the science of this and communicating, exposing some of the BS and the sort of the natural, just like in the AI space, the natural charlatanism, if that's a word, in quantum mechanics in general, but quantum computers and so on. Can you give some notes about people or ideas that people like me or listeners in general from outside the field should be cautious of when they're taking in news headings that Google achieved quantum supremacy? So what should we look out for? Where's the charlatans in the space? Where's the BS?
Yeah. So, good question. Unfortunately, quantum computing is a little bit like cryptocurrency or deep learning. Like there is a core of something that is genuinely revolutionary and exciting, and because of that core, it attracts this sort of vast penumbra of people making just utterly ridiculous claims. And so with quantum computing, I mean, I would say that the main way that people go astray is by, not focusing on sort of the question of, are you getting a speed up over a classical computer or not, right? And so people have like dismissed quantum supremacy because it's not useful, right? Or, it's not itself, let's say, obviously useful for anything. Okay, but ironically, these are some of the same people who will go and say, well, we care about useful applications. We care about solving traffic routing and and financial optimization and all these things. And that sounds really good, but their entire spiel is sort of counting on nobody asking the question, yes, but how well could a classical computer do the same thing?
Yes.
Right.
Yeah.
I really mean the entire thing is they say, well, a quantum computer can do this, a quantum computer can do that. Right. And they just avoid the question, are you getting a speed up over a classical computer or not? And, if so, how do you know? Have you really thought carefully about classical algorithms to do, to solve the same problem, right? And a lot of the application areas that, companies and investors are most excited about, that the popular press is most excited about, for quantum computers have been things like machine learning, AI, optimization. Okay. And the problem with that is that since the very beginning, even if you have a perfect, fault tolerant, scalable quantum computer, we have known of only modest speed ups that you can get for these problems. Okay. So there is a famous quantum algorithm called Grover's algorithm. Okay. And what it can do is it can solve many, many of the problems that arise in AI, machine learning, optimization, including NP-complete problems. Okay. But it can solve them in about the square root of the number of steps that a classical computer would need for the same problems. Okay, now a square root speed up is, important. It's impressive. It is not an exponential speed up. Okay, so it is not the kind of game changer that, let's say, Shor's algorithm for factoring is, or for that matter, that simulation of quantum mechanics is. Okay, it is a more modest speed up. Let's say, roughly, in theory, it could roughly double the size of the optimization problems that you could handle, right? And so, because people found that, I guess, too boring or too unimpressive, they've gone on to like invent all of these heuristic algorithms where, because no one really understands them, you can just project your hopes onto them, right? That, well, maybe it gets an exponential speed up. You can't prove that it doesn't,
Right.
and the burden is on you to prove that it doesn't get a speed up, right? And, so they've done an immense amount of that kind of thing. And a really worrying amount of the case for building a quantum computer has come to rest on this stuff that those of us in this field know perfectly well is on extremely shaky foundations.
So the fundamental question is, show that there's a speed up over the classical.
Absolutely.
And in the space that you're referring to, which is actually really interesting, so the area that a lot of people are excited about is machine learning.
Yeah.
So your sense is, do you think it will... So I know that there's a lot of smoke currently.
Yeah.
But do you think there actually eventually might be breakthroughs where you do get exponential speed ups in the machine learning space?
Absolutely, there might be. I mean, I think we know of modest speed ups that you can get for these problems. I think, whether you can get bigger speed ups is one of the biggest questions for quantum computing theory, for people like me to be thinking about. Now, we had actually recently a really, a super exciting candidate for an exponential quantum speed up for a machine learning problem that people really care about. This is basically the Netflix problem, the problem of recommending products to users given some sparse data about their preferences. Karanitis and Prakash in 2016 had an algorithm for sampling recommendations that was exponentially faster than any known classical algorithm, right? And so, a lot of people were excited. I was excited about it. I had an 18-year-old undergrad by the name of Ewin Tang, and she was obviously brilliant. She was looking for a project. I gave her as a project, can you prove that this speed up is real? Can you prove that any classical algorithm would need to access exponentially more data, right? And this was a case where if that was true, this was not like a P versus NP type of question, right? This might well have been provable, but she worked on it for a year. She couldn't do it. Eventually, she figured out why she couldn't do it, and the reason was that was false. There is a classical algorithm with a similar performance to the quantum algorithm. So Ewin succeeded in dequantizing that machine learning algorithm. And then in the last couple of years, building on Ewin's breakthrough, a bunch of the other quantum machine learning algorithms that were proposed have now also been dequantized.
Yeah.
Okay.
Well,
and so I would say,
kind of an important backward step.
Yes.
Yes, or a forward step for science, but a step for quantum machine learning.
Yeah.
That precedes the big next forward step.
Right.
If it's possible.
Right. Now, some people will say, well, there's a silver lining in this cloud. They say, well, look, thinking about quantum computing has led to the discovery of potentially useful new classical algorithms.
That's true.
Right. And so, so you get these spin-off applications. But if you want a quantum speed up, you really have to think carefully about that. Ewin's work was a perfect illustration of why. Right. And I think that, the challenge, the field is now open, right? Find a better example. Find, where quantum computers are going to deliver big gains for machine learning. I am, not only do I ardently support, people thinking about that, I'm trying to think about it myself and have my students and postdocs think about it. But we should not pretend that those speed ups are already established. And the problem comes when so many of the companies and journalists in this space are pretending. Yeah.
You just mentioned a million things. Well, I'll backtrack for a second.
Yeah, sure.
So we're in these vacuum tube days.
Yeah. Just entering them.
And just entering. Wow. Okay. So
yeah.
How do we escape the vacuum? So how do we get to where we are now with the CPU? Is this a fundamental engineering challenge? Is there breakthroughs on the physics side that they're needed on the computer science side? Is it a financial issue where much larger, just sheer investment and excitement is needed?
So those are excellent questions. My guess,
no answers.
my guess would be all of the above.
Yeah.
I mean, my guess, you could say fundamentally it is an engineering issue, right? The theory has been in place since the 90s, at least, this is what, error correction would look like. We do not have the hardware that is at that level, but at the same time, so you could just, try to power through, maybe even like, if someone spent $1 trillion on some quantum computing Manhattan project, right, then conceivably they could just, build an error corrected quantum computer as it was envisioned back in the 90s, right? I think the more plausible thing to happen is that there will be further theoretical breakthroughs and there will be further insights that will cut down the cost of doing this.
Andrew Yang, a very intelligent and a presidential candidate with a lot of interesting ideas in all kinds of technological fields, tweeted that because of quantum computing, no code is uncrackable. Is he wrong or right?
He was premature, let's say. Wrong. So look, I'm a fan of Andrew Yang. I like his I like his ideas. I like his candidacy. I think that he may be ahead of his time with the universal basic income and so forth, and he may also be ahead of his time in that tweet that you referenced. So regarding using quantum computers to break cryptography, so the situation is this.
Yeah. Yeah.
Okay, so the famous discovery of Peter Shor, 26 years ago, that really started quantum computing, as an autonomous field, was that if you built a full scalable quantum computer, then you could use it to efficiently find the prime factors of huge numbers and calculate discrete logarithms and solve a few other problems that are very, very special in character, right? They're not NP-complete problems. We're pretty sure they're not, okay? But it so happens that most of the public key cryptography that we currently use to protect the internet is based on the belief that these problems are hard.
Yeah.
Okay, what Shor showed is that once you get scalable quantum computers, then that's no longer true. Okay, but now before people panic, there are two important points to understand here. Okay, the first is that quantum supremacy, the milestone that Google just achieved, is very, very far from the kind of scalable quantum computer that would be needed to actually threaten public key cryptography. Okay, so, we touched on this earlier, right? But Google's device has 53 physical qubits, right? To threaten cryptography, you're talking, with any of the known error correction methods, you're talking millions of physical qubits.
Because error correction would be required to threaten cryptography.
Yes. Yes. It certainly would, right? And how much, how great will the overhead be from the error correction? That we don't know yet. But with the known codes, you're talking millions of physical qubits and of a much higher quality than any that we have now. Okay, so I don't think that is coming soon. Although people who have secrets that need to stay secret for 20 years, are already worried about this. For the good reason that we presume that intelligence agencies are already scooping up data, in the hope that eventually they'll be able to decode it once quantum computers become available. Okay, so this brings me to the second point I wanted to make, which is that there are other public key crypto systems that are known that we don't know how to break even with quantum computers. Okay, and there's a whole field devoted to this now, which is called post-quantum cryptography. Okay, and so there is already so we have some good candidates now. The best known being what are called lattice-based crypto systems. And there is already some push to try to migrate to these crypto systems. So NIST in the US is holding a competition to create standards for post-quantum cryptography, which will be the first step in trying to get every web browser and every router to upgrade, and use something like SSL that would be based on what we think is quantum secure cryptography. But this will be a long process. But it is something that people are already starting to do, and so I'm Shor's algorithm was sort of a dramatic discovery. It could be a big deal for whatever intelligence agency first gets a scalable quantum computer, if no one else knows that they have it, right? But eventually, we think that we could migrate the internet to the post-quantum cryptography, and then we'd be more or less back where we started. Okay, so this is sort of not the application of quantum computing, I think, that's really going to change the world in a sustainable way, right? By the way, the biggest practical application of quantum computing that we know about by far, I think, is simply the simulation of quantum mechanics itself. In order to, learn about chemical reactions, design maybe new chemical processes, new materials, new drugs, new solar cells, new superconductors, all kinds of things like that.
What's the size of a quantum computer that would be able to simulate the quantum mechanical systems themselves that would be impactful for the real world for the kind of chemical reactions and that kind of work? What scale are we talking about?
Now you're asking a very, very current question, a very big question. People are going to be racing over the next decade to try to do useful quantum simulations, even with 100 or 200 qubit quantum computers of the sort that we expect to be able to build over the next decade. Okay, so that might be, the first application of quantum computing that we're able to realize, or maybe it will prove to be too difficult. And maybe even that will require fault tolerance or, will require error correction.
So there's an aggressive race to come up with the one case study, kind of like with the Peter Shor, with the idea that would just capture the world's imagination of look, we can actually do something very useful here.
Right. But I think, within the next decade, the best shot we have is certainly not, using Shor's algorithm to break cryptography, it's just because it requires, too much in the way of error correction. The best shot we have is to do some quantum simulation that tells the material scientists or chemists or nuclear physicists, something that is useful to them and that they didn't already know. And you might only need one or two successes in order to change some, billion-dollar industries, right? Like, the way that people make fertilizer right now is still based on the Haber-Bosch process from a century ago. And it is some many-body quantum mechanics problem that no one really understands, right? If you could design a better way to make fertilizer, right, that's, billions of dollars right there. So, exactly. Those are sort of the applications that people are going to be aggressively racing toward over the next decade. Now, I don't know if they're going to realize it or not, but it is, they certainly at least have a shot. So it's going to be a very, very interesting next decade.
But just to clarify, what's your intuition? Is if a breakthrough like that comes, is it possible for that breakthrough to be on 50 to 100 qubits, or is scale a fundamental thing, like a 500, 1,000 plus qubits?
Yeah, so I can tell you what the current studies are saying. I think probably better to rely on that than on my intuition. But there was a group at Microsoft had a study a few years ago that said even with only about 100 qubits, you could already learn something new about this, the chemical reaction that makes fertilizer, for example. The trouble is they're talking about 100 qubits and about 1 million layers of quantum gates. Okay, so basically they're talking about 100 nearly perfect qubits.
So the logical qubits, as you mentioned before.
Exactly, 100 logical qubits. And now, the hard part for the next decade is going to be, well, what can we do with 100 to 200 noisy qubits?
Yeah.
Yeah.
Is there error correction breakthroughs that might come without the need to do thousands or millions of physical qubits?
Yeah, so people are going to be pushing simultaneously on a bunch of different directions. Yeah. One direction, of course, is just making the qubits better, right? And there is tremendous progress there. I mean, the fidelities, like the accuracy of the qubits, has improved by several orders of magnitude. In the last decade or two. Okay, the second thing is designing better error, or let's say lower overhead error correcting codes. And even short of doing the full recursive error correction, there are these error mitigation strategies that you can use, that may, allow you to eke out a useful speed up in the near term. And then the third thing is just taking the quantum algorithms for simulating quantum chemistry or materials and making them more efficient. And those algorithms are already dramatically more efficient than they were, let's say, 5 years ago. And so when, I quoted these estimates like a circuit depth of 1 million. And so, I hope that because people will care enough that these numbers are going to come.
Quantum state.
Is it useful for us to maybe first talk about how quantum mechanics fits into the Wolfram physics model?
Yes.
Let's go there. So we talked about general relativity. Now, what have you found?
What's the story of quantum mechanics? Right.
Within and outside of the Wolfram physics.
Right. So, I mean, the key idea of quantum mechanics, the sort of the typical interpretation is classical physics says a definite thing happens. Quantum physics says there's this whole set of paths of things that might happen, and we are just observing some overall probability of how those paths work. Okay, so when you think about our hypergraphs and all these little updates that are going on, there's a very remarkable thing to realize, which is if you say, well, which particular sequence of updates should you do? Say, well, it's not really defined. You can do any of a whole collection of possible sequences of updates. Okay, that set of possible sequences of updates defines yet another kind of graph that we call a multi-way graph. And a multi-way graph just is a graph where at every node there is a choice of several different possible things that could happen. So, for example, you go this way, you go that way. Those are two different edges in the multi-way graph. And you're building up this set of possibilities. So actually, like, for example, I just made the multi-way graph for tic-tac-toe. Okay, so tic-tac-toe, you start off with some board that, is everything is blank, and then somebody can put down an X somewhere, an O somewhere, and then there are different possibilities. At each stage, there are different possibilities. And so you build up this multi-way graph of all those possibilities. Now, notice that even in tic-tac-toe, you have the feature that there can be something where you have two different things that happen, and then those branches merge because you end up with the same shape of, the same configuration of the board, even though you got there in two different ways. So the thing that's sort of an inevitable feature of our models is that just like quantum mechanics suggests, definite things don't happen. Instead, you get this whole multi-way graph of all these possibilities. Okay, so then the question is, so that's sort of a picture of what's going on. Now you say, okay, well, quantum mechanics has all these features of, all this mathematical structure and so on. How do you get that mathematical structure? Okay, couple of things to say. So quantum mechanics is actually, in a sense, two different theories glued together. Quantum mechanics is the theory of how quantum amplitudes work, that more or less give you the probabilities of things happening. And it's the theory of quantum measurement, which is the theory of how we actually conclude definite things. Because the mathematics just gives you these quantum amplitudes, which are more or less probabilities of things happening, but yet we actually observe definite things in the world. Quantum measurement has always been a bit mysterious. It's always been something where people just say, well, the mathematics says this, but then you do a measurement and there are philosophical arguments about what the measurement is, but it's not something where there's a theory of the measurement.
Somebody on Reddit also asked, please ask Stephen to tell his story of the double slit experiment.
Okay. Yeah, I can.
Does that make sense?
Oh, yeah, it makes sense. Absolutely makes sense.
Why is this like a good way to discuss?
A little bit. Let me explain a couple of things first. So the structure of quantum mechanics is mathematically quite complicated. One of the features, let's see, well, how to describe this. Okay, so first point is there's this multi-way graph of all these different paths of things that can happen in the world. And the important point is that these, you can have branchings and you can have mergings. Okay, so this property turns out causal invariance is the statement that the number of mergings is equal to the number of branchings.
Yeah.
So in other words, every time there's a branch, eventually there will also be a merge. In other words, every time there were two possibilities for what might have happened, eventually those will merge.
Yeah. Beautiful concept, by the way. But yeah.
So that idea. Okay. So then, so that's one thing, and that's closely related to the sort of objectivity in quantum mechanics. The fact that we believe definite things happen. It's because although there are all these different paths, in some sense, because of causal invariance, they all imply the same thing. I'm cheating a little bit in saying that, but that's roughly the essence of what's going on. Okay. Next thing to think about is. You have this multi-way graph. It has all these different possible things that are happening. Now we ask, this multi-way graph is sort of evolving with time. Over time, it's branching, it's merging, it's doing all these things. Okay. The question we can ask is, if we slice it at a particular time, what do we see? And that slice represents, in a sense, something to do with the state of the universe at a particular time. So in other words, we've got this multi-way graph of all these possibilities, and then we're asking, okay, we take this slice. This slice represents, okay, each of these different paths corresponds to a different quantum possibility for what's happening.
Right.
When we take this slice, we're saying, what are the set of quantum possibilities that exist at a particular time?
And when you say slice, are these, you slice the graph and then there's a bunch of leaves?
A bunch of leaves.
And those represent the state of things.
Right, but then, okay, so the important thing that you are quickly picking up on is that what matters is kind of how these leaves are related to each other. So a good way to tell how leaves are related is just to say, on the step before, did they have a common ancestor? So two leaves they might have just branched from one thing, or they might be far away, way far apart in this graph, where to get to a common ancestor, maybe you have to go all the way back to the beginning of the graph, all the way back to the beginning.
So there's some kind of measure of distance.
Right. What you get is by making this slice, what you call it branchial space, the space of branches. And in this branchial space, you have a graph that represents the relationships between these quantum states in branchial space. You have this notion of distance in branchial space. Okay, so
it's connected to quantum entanglement.
Yes, yes. It's basically the distance in branchial space is kind of an entanglement distance. So that's
a very nice model.
Right. It is very nice. It's very beautiful. It's so clean. I mean, it's really, and it tells one, okay, so anyway, so then this branchial space has this sort of map of the entanglements between quantum states. Yes. So in physical space, we have, you can take, let's say, the causal graph, and we can slice that at a particular time, and then we get this map of how things are laid out in physical space. When we do the same kind of thing, there's a thing called the multi-way causal graph, which is the analog of a causal graph for the multi-way system. We slice that. We get essentially the relationships between things, not in physical space, but in the space of quantum states. It's like which quantum state is similar to which other quantum state. Okay, so now I think next thing to say is just to mention how quantum measurement works. So quantum measurement has to do with reference frames in branchial space. So measurement in physical space, it matters how we assign spatial position and how we define coordinates in space and time. And that's how we make measurements in ordinary space. Are we making a measurement based on us sitting still here? Are we traveling at half the speed of light and making measurements that way? These are different reference frames in which we're making our measurements. And the relationship between different events and different points in space and time will be different depending on what reference frame we're in. Okay, so then we have this idea of quantum observation frames, which are the analog of reference frames, but in branchial space. And so what happens is, what we realize is that a quantum measurement is the observer is sort of arbitrarily determining this reference frame. The observer is saying, I'm going to understand the world by saying that space and time are coordinatized this way. I'm going to understand the world by saying that quantum states and time are coordinatized in this way. And essentially what happens is that the process of quantum measurement is a process of deciding how you slice up this multi-way system in these quantum observation frames. So in a sense, the way the observer enters is by their choice of these quantum observation frames. And what happens is that the observer, this is again another stack of other concepts, but anyway, because the observer is computationally bounded, there is a limit to the type of quantum observation frames that they can construct.
Interesting. Okay, so there's some constraints, some limit on
the
choice of observation frames.
Right. And by the way, I just want to mention that it's bizarre, but there's a hierarchy of these things. So in thermodynamics, the fact that we believe entropy increases, we believe things get more disordered, is a consequence of the fact that we can't track each individual molecule. If we could track every single molecule, we could run every movie in reverse, so to speak, and we would not see that things are getting more disordered. But it's because we are computationally bounded. We can only look at these big blobs of what all these molecules collectively do, that we think that that we describe it in terms of entropy increasing and so on. And it's the same phenomenon, basically, also a consequence of computational irreducibility that causes us to basically be forced to conclude that definite things happen in the world, even though there's this quantum, this set of all these different quantum processes that are going on. So, I'm skipping a little bit, but that's a rough picture.
And in the evolution of the Wolfram Physics project, where do you feel we stand on some of the puzzles that are along the way? So you're skipping along a bunch of
It's
stuff.
amazing how much these things are unraveling. I mean, these things, look, it used to be the case that I would agree with Dick Feynman, nobody understands quantum mechanics, including me.
Yeah.
Okay? I'm getting to the point where I think I actually understand quantum mechanics. My exercise, okay, is can I explain quantum mechanics for real at the level of kind of middle school type explanation?
Right.
And I'm getting closer. It's getting there. I'm not quite there. I've tried it a few times, and I realize that there are things that where I have to start talking about elaborate mathematical concepts and so on. But I think, and you've got to realize that it's not self-evident that we can explain, at an intuitively graspable level something which, about the way the universe works. The universe wasn't built for our understanding, so to speak. But I think then okay. So another important idea is this idea of branchial space, which I mentioned, this sort of space of quantum states. It is, okay, so I mentioned Einstein's equations describing, the effect of mass and energy on trajectories of particles, on GD6. The curvature of physical space is associated with the presence of energy according to Einstein's equations. Okay, so it turns out that, rather amazingly, the same thing is true in branchial space. So it turns out the presence of energy, or more accurately, Lagrangian density, which is a kind of relativistic invariant version of energy, the presence of that causes essentially deflection of GD6 in this branchial space. Okay, so you might say, so what? Well, it turns out that the best formulation we have of quantum mechanics, the Feynman path integral, is a thing that describes quantum processes in terms of mathematics that can be interpreted as, well, in quantum mechanics, the big thing is you get these quantum amplitudes, which are complex numbers that represent, when you combine them together, represent probabilities of things happening. Mm-hmm. And so the big story has been, how do you derive these quantum amplitudes? And people think these quantum amplitudes, they have a complex number, has, real part and imaginary part. You can also think of it as a magnitude and a phase. And people have sort of thought these quantum amplitudes have magnitude and phase, and you compute those together. Turns out that the magnitude and the phase come from completely different places. The magnitude comes, okay, so how do you compute things in quantum mechanics? Roughly, I'm telling you, I'm getting there to be able to do this at a middle school level, but I'm not there yet. Roughly what happens is you're asking, does this state in quantum mechanics evolve to this other state in quantum mechanics? Mm-hmm. And you can think about that like a particle traveling, or something traveling through physical space, but instead it's traveling through branchial space. Mm-hmm. And so what's happening is, does this quantum state evolve to this other quantum state? It's like saying, does this object move from this place in space to this other place in space? Okay. Now, the way that these quantum amplitudes characterize kind of to what extent the thing will successfully reach some particular point in branchial space. Just like in physical space, you could say, oh, it had a certain velocity and it went in this direction. In branchial space, there's a similar kind of concept.
Is there a nice way to visualize, for me now, mentally branchial space?
It's just, you have this hypergraph, you have this multi-way graph. It's this big branching and merging thing.
But I mean, moving through that space. I'm just trying to understand what that looks like.
Space is probably exponential dimensional, which makes it, again, another can of worms in understanding what's going on. That space, as in ordinary space, this hypergraph, the spatial hypergraph, limits to something which is like a manifold, like something like three-dimensional space. Almost certainly, the multi-way graph limits to a Hilbert space, which is something that, I mean, it's just a weirder exponential dimensional space. And by the way, you can ask, I mean, there are much weirder things that go on. For example, one of the things I've been interested in is the expansion of the universe in branchial space. So we know the universe is expanding in physical space, mm-hmm. but the universe is probably also expanding in branchial space. So that means the number of quantum states of the universe is increasing with time.
The diameter of the thing is growing.
Right. So that means that the And by the way, this is related to whether quantum computing can ever work.
Why?
Okay, so let me explain why. So let's talk about. Okay, so first of all, just to finish the thought about quantum amplitudes, the incredibly beautiful thing. I'm just very excited about this. The Feynman path integral is this formula. It says that the amplitude, the quantum amplitude, is e to the I s over h bar, where s is this thing called the action, and okay, so that can be thought of as representing a deflection of the angle of this path in the multiway graph. So it's a deflection of a geodesic in the multiway path that is caused by this thing called the action, which is essentially associated with energy. Okay? And so this is a deflection of a path in branchial space that is described by this path integral, which is the thing that is the mathematical essence of quantum mechanics. Turns out that deflection is the deflection of geodesics in branchial space follows the exact same mathematical setup as the deflection of geodesics in physical space, except the deflection of geodesics in physical space is described with Einstein's equations. The deflection of geodesics in branchial space is defined by the Feynman path integral, and they are the same. In other words, they are mathematically the same. So that means that general relativity is a story of essentially motion in physical space. Quantum mechanics is a story of essentially motion in branchial space. And the underlying equation for those two things, although it's presented differently because one's interested in different things in branchial space than in physical space, but the underlying equation is the same. So in other words, it's just, these two theories, which are the two sort of pillars of 20th century physics, which have seemed to be off in different directions, are actually facets of the exact same theory. And this,
that's exciting to see where that evolves, and exciting that just is there.
Right. I mean, to me, look, having spent some part of my early life, working in the context of these theories of 20th century physics, they seem so different, and the fact that they're really the same is just really amazing.
So, quantum computers.
Okay, so the basic idea of quantum computers, the promise of quantum computers is quantum mechanics does things in parallel, and so you can sort of intrinsically do computations in parallel, and somehow that can be much more efficient than just doing them one after another. And, I actually worked on quantum computing a bit with Dick Feynman back in 1981, 2, 3, that kind of time frame. And we...
A fascinating image. You and Feynman working on quantum computers.
Well, we tried to work, the big thing we tried to do was invent a randomness chip that would generate randomness at a high speed using quantum mechanics. And the discovery that wasn't really possible was part of the story of, we never really wrote anything about it. I think maybe he wrote some stuff, but we didn't write stuff about what we figured out about sort of the fact that it really seemed like the measurement process in quantum mechanics was a serious damper on what was possible to do in sort of, the possible advantages of quantum mechanics for computing. But anyway, so the sort of the promise of quantum computing is, let's say you're trying to, factor an integer. Well, you can, instead of, when you factor an integer, you might say, well, does this factor work? Does this factor work? Does this factor work? In ordinary computing, it seems like we pretty much just have to try all these different factors, kind of one after another. But in quantum mechanics, you might have the idea, you can just sort of have the physics try all of them in parallel. Mm-hmm. Okay? And and there's this algorithm, Shor's algorithm, which allows you, according to the formalism of quantum mechanics, to do everything in parallel and to do it much faster than you can on a classical computer. Mm-hmm. Okay. The only little footnote is you have to figure out what the answer is. You have to measure the result. So the quantum mechanics internally has figured out all these different branches, but then you have to pull all these branches together to say, and the classical answer is this. Okay? The standard theory of quantum mechanics does not tell you how to do that. It tells you how the branching works, but it doesn't tell you the process of corralling all these things together. And that process, which intuitively you can see is going to be kind of tricky, but our model actually does tell you how that process of pulling things together works. And the answer seems to be, we're not absolutely sure. We've only got to 2 times 3 so far which is kind of in this factorization in quantum computers. But we can what seems to be the case is that the advantage you get from the parallelization from quantum mechanics is lost from the amount that you have to spend pulling together all those parallel threads to get to a classical answer at the end. Now, that phenomenon is not unrelated to various decoherence phenomena that are seen in practical quantum computers and so on. I mean, I should say, as a very practical point, I mean, it's like, should people stop bothering to do quantum computing research? No, because what they're really doing is they're trying to use physics to get to a new level of what's possible in computing. And that's a completely valid activity. Whether you can really put, whether you can say, oh, you can solve an NP-complete problem, you can reduce exponential time to polynomial time, we're not sure. And I'm suspecting the answer is no, but that's not relevant to the practical speed-ups you can get by using different kinds of technologies, different kinds of physics to do basic computing.
But so you're saying, I mean, some of the models you're playing with, the indication is that to get all the sheep back together to corral everything together to get the actual solution to the algorithm is
you lose all the
you use all of the.
By the way, I mean, so again, this question: do we actually know what we're talking about quantum computing and so on? So again, we're doing proof by compilation. So we have a quantum computing framework in Wolfram language, which is a standard quantum computing framework that represents things in terms of the standard formalism of quantum mechanics, and we have a compiler that simply compiles the representation of quantum gates into multi-way systems. So, and in fact, the message that I got was from somebody who's working on the project who has managed to compile one of the sort of a core formalism based on category theory, of core quantum formalism into multi-way systems. So
when you say multi-way system, these multi-way graphs?
Yes.
So you're okay, that's awesome. And then you can do all kinds of experiments on that multi-way graph.
Right. Well, but the point is that what we're saying is we've got this representation of, let's say, Shor's algorithm in terms of standard quantum gates. And it's just a pure matter of sort of computation to just say that is equivalent. We will get the same result as running this multi-way system.
Can you do complexity analysis on that multi-way system?
Well, that's what we've been trying to do. Yes. We're getting there. We haven't done that yet. I mean, there's a pretty good indication of how that's going to work out. And we've done it, as I say, our computer experiments, we've unimpressively gotten to about 2 times 3 in terms of factorization, which is kind of about how far people have got with physical quantum computers as well. But that's but yes, we definitely will be able to do complexity analysis, and we will be able to know. So the one remaining hope for quantum computing really, really working at this formal level of, quantum brand, exponential stuff being done in polynomial time and so on, the one hope, which is very bizarre, is that you can piggyback on the expansion of branchial space. So here's how that might work. So you think, energy conservation, standard thing in high school physics, energy is conserved, right? But now you think about energy in the context of cosmology, in the context of the whole universe. It's a much more complicated story. The expansion of the universe kind of violates energy conservation. And so, for example, if you imagine you've got 2 galaxies, they're receding from each other very quickly. They've got 2 big central black holes. You connect a spring between these 2 central black holes. Not easy to do in practice, but let's imagine you could do it. Now, that spring is being pulled apart. It's getting more potential energy in the spring as a result of the expansion of the universe. So, in a sense, you are piggybacking on the expansion that exists in the universe and the sort of violation of energy conservation that's associated with that cosmological expansion to essentially get energy. You're essentially building a perpetual motion machine by using the expansion of the universe. And that is a physical version of that. It is conceivable that the same thing can be done in branchial space to essentially mine the expansion of the universe in branchial space as a way to get quantum computing for free, so to speak, just from the expansion of the universe in branchial space. Now, the physical space version is kind of absurd and involves, springs between black holes and so on. it's conceivable that the branchial space version is not as absurd, and that it's actually something you can reach with physical things you can build in labs and so on. We don't know yet.
Okay, so like you were saying, the branchial space might be expanding, and there might be something that could be exploited.
Right, in the same kind of way that you can exploit the that expansion of the universe in principle in physical space.
You just have like a glimmer of hope.
Right. I think that the real answer is going to be that for practical purposes, the official brand that says you can do exponential things in polynomial time is probably not going to work in some sense.
Okay, so that's general relativity. And what's its friendly neighbor? Like you said,
Quantum
there's two
mechanics.
theories, quantum mechanics.
Right. So quantum mechanics, the sort of the way that originated was, one question was, is the world continuous or is it discrete? In ancient Greek times, people had been debating this. People debated it, throughout history. Is light made of waves? Is it continuous? Is it discrete? Is it made of particles, corpuscles, whatever? What had become clear in the 1800s is that atoms, materials are made of discrete atoms. When you take some water, the water is not a continuous fluid, even though it seems like a continuous fluid to us at our scale. But if you say, let's look at it smaller and smaller and smaller and smaller scale, eventually you get down to these molecules and then atoms. It's made of discrete things. So the question is sort of how important is this discreteness? Just what's discrete, what's not discrete? Is energy discrete? What's discrete, what's not? And so,
does it have mass? Those kinds of questions.
Yeah, right. Well, there's question. I mean, for example, is mass discrete? Is an interesting question, which is now something we can address. But what happened in the coming up to the 1920s, there was this kind of mathematical theory developed that could explain certain kinds of discreteness particularly in features of atoms and so on. And what developed was this mathematical theory that was the theory of quantum mechanics, theory of wave functions, Schrodinger's equation, things like this. That's a mathematical theory that allows you to calculate lots of features of the microscopic world, lots of things about how atoms work, et cetera, et cetera, et cetera. Now, the calculations all work just great. The question of what does it really mean is a complicated question. Now, I mean, to just explain a little bit historically, the early calculations of things like atoms worked great in the 1920s, 1930s, and so on. There was always a problem. There were, in quantum field theory, which is a theory of, in quantum mechanics, you're dealing with a certain number of electrons, and you fix the number of electrons. You say, I'm dealing with a 2-electron thing. In quantum field theory, you allow for particles being created and destroyed. So you can emit a photon that didn't exist before, you can absorb a photon, things like that. That's a more complicated, mathematically complicated theory, and it had all kinds of mathematical issues and all kinds of infinities that cropped up. And it was finally figured out more or less how to get rid of those. But there were only certain ways of doing the calculations, and those didn't work for atomic nuclei, among other things. And that led to a lot of development up until the 1960s of alternative ideas for how one could understand what was happening in atomic nuclei, et cetera, et cetera, et cetera. End result, in the end, the kind of most, quotes, obvious mathematical structure of quantum field theory seems to work, although it's mathematically difficult to deal with. But you can calculate all kinds of things. You can calculate to, a dozen decimal places, certain things. You can measure them. It all works. It's all beautiful. Now you say
the underlying fabric is the model of that particular theory is fields. Like you keep saying fields.
Those are quantum fields. Those are different from classical fields. A field is something like you say, there's, like you say, the temperature field in this room. It's like there is a value of temperature at every point around the room. That's or you can say the wind field would be the vector direction of the wind at every point.
It's continuous.
Yes, and that's a classical field. A quantum field is a much more mathematically elaborate kind of thing. And I should explain that one of the pictures of quantum mechanics that's really important is, in classical physics, one believes that sort of definite things happen in the world. You pick up a ball, you throw it, the ball goes in a definite trajectory it has certain equations of motion, it goes in a parabola, whatever else. In quantum mechanics, the picture is definite things don't happen. Instead, sort of what happens is this whole sort of structure of all, many different paths being followed And we can calculate certain aspects of what happens, certain probabilities of different outcomes and so on. And you say, well, what really happened? What's really going on? What's the sort of what's the underlying, what's the underlying story? How do we turn this mathematical theory that we can calculate things with into something that we can really understand and have a narrative about? And that's been really, really hard for quantum mechanics. My friend Dick Feynman always used to say, nobody understands quantum mechanics, even though he'd made his whole career out of calculating things about quantum mechanics. So it's a
But
little.
nevertheless, it's what the quantum field theory is very, very accurate at predicting a lot of the physical phenomena. So it works.
Yeah, but there are things about it. It has certain. When we apply it, the standard model of particle physics, for example, which we apply to calculate all kinds of things, it works really well. And you say, well, it has certain parameters. It has a whole bunch of parameters, actually. You say, why does the muon particle exist? Why is it 206 times the mass of the electron? We don't know. No.
So, we're talking about randomness. I wonder if I can weave in quantum mechanics for a brief moment. There's a lot of advancements on the quantum computing side. So leveraging quantum mechanics to perform a new kind of computation, and there's concern of that being a threat to a lot of the basic assumptions that underlie cryptography. What do you think? Do you think quantum computing will challenge a lot of cryptography? Will cryptography be able to defend all those kinds of things?
Okay, great. So first of all, for the record, not because I think it matters, but it's important that the record, there are people who continue to contend that quantum mechanics exist, but has nothing to do with computing, is not going to accelerate it, at least, very basic, hard computation. That is a belief, you cannot take it out. I'm a little bit more agnostic about it, but I really believe, going back to whatever I said about the one-way function.
Mm-hmm.
So one-way function, what is it? That is a cryptography. So does quantum computing challenge
the one-way function?
Essentially, you can boil it down to, does quantum computing find a one-way function? What is a one-way function? Easy in one direction, hard in the other. Okay, but if quantum computing exists, when you define what it is easy, is not easy by a classical computer and hard by a classical computer, but easy for a quantum computer. That's a bad idea. But once easy means it should be easy for a quantum and hard for also quantum.
Mm-hmm.
Then you can see that you are, yes, it's a challenge, but you have hope because you can absorb, if quantum computing really realizes and becomes available according to the promises, then you can use them also for the easy part.
Mm-hmm.
And once you use it for the easy part, the choices that you have a one-way function, they multiply. So the particular candidates of one-way function may not be one-way anymore, but quantum one-way function may continue to exist. And so I really believe that for life to be meaningful with one-way function had to exist. Because just imagine that anything that is becomes easy to do. I mean, what kind of life is it? I mean, so you need that. And if something is hard, but it's so hard to generate, you'll never find something which is hard for you. You want that there is abundance, there is easy to produce, hard problem. That's my opinion is why life is interesting, because hard problems pop up at a really relative speed. So in some sense, I almost think that I do hope they exist. If they don't exist, somehow life is way less interesting than it actually is.
Yeah, it does. That's funny. It does seem like the one-way function is fundamental to all of life, which is the emergence of the complexity that we see around us seem to require the one-way function. I don't know if you play with cellular automata. That's just another formulation of.
I know, but that's
a very simple. It's almost a very simple illustration of starting out with simple rules and one way, being able to generate incredible amounts of complexity, but then you ask the question, can I reverse that? And it's just surprising how difficult it is to reverse that. It's surprising, even in constrained situations, it's very difficult to prove anything. That it almost, I mean, the sad thing about it, well, I don't know if it's sad, but it seems like we don't even have the mathematical tools to reverse engineer stuff. I don't know if they exist or not. But in the space of cellular automata, when you start with something simple and you create something incredibly complex, can you take a small picture of that complex and reverse engineer? That's kind of what we're doing as scientists. You're seeing the result of the complexity, and you're trying to come up with some universal law that generate all of this. What is the theory of everything? What are the basic physics laws that generate this whole thing? And there's a hope that you should be able to do that, but it's difficult.
Yeah, but there is also some poetry of the fact that it's difficult,
right?
Because it gives us some mystery to life, which without which, I mean, it's not so fun. Right? Life would not be
the solar system.
You mentioned quantum mechanics, and we're talking about cosmic scale objects. You've talked about that the evolution of astrophysical disks can be modeled with Schrodinger's equation.
I sure did.
Why? It's like, how does quantum mechanics become relevant when you consider the evolution of objects in the solar system?
Yeah. Well, let me take a step back and just say, like, I remember being, utterly confused by quantum mechanics when I first learned it. And the Schrodinger equation, which is kind of the parent equation of that whole field, seems to come out of nowhere. Right. The way that I was sort of explaining it, I remember asking, my professor, I was like, but where does it come from? He's like, well, just like, don't worry about it, and just like calculate the hydrogen, energy levels. Right. So it's like I could do all the problems. I just did not have any intuition for where this parent, super important equation came from. Now, down the line, I was preparing for my own lecture, and I was trying to understand how waves travel in self-gravitating disks. So, again, there's a very broad theory that's already developed, but I was looking for some simpler way to explain it, really, for the purposes of teaching class. And so I thought, okay, what if I just imagine a disk as an infinite number of concentric circles, right, that interact with each other gravitationally? That's a problem in some sense that I can solve using methods from like the late 1700s. Right? So I can write down Hamiltonian. Well, I can write down the energy function basically of their interactions. And what I found is that when you take the continuum limit, when you go from discrete circles that are talking to each other gravitationally to a continuum disk, suddenly this gravitational interaction among them, right, the governing equation becomes the Schrodinger equation. Yeah. And I had to think about that for a little bit.
Did you just unify quantum mechanics and gravity?
No, this is not the same thing as like, fusing relativity and quantum mechanics. But it did get me thinking a little bit. So the fact that waves in astrophysical disks behave just like wave functions of particles is kind of like an interesting analogy, because for me it's easier to imagine waves traveling through, astrophysical disks, or really just sheets of paper. And the reason this is that analogy exists is because there's actually nothing quantum about the Schrodinger equation. The Schrodinger equation is just a wave equation, and all of the interpretation that comes from it is quantum, but the equation itself is not a quantum being.
So you can use it to model waves. It's not turtles, it's waves all the way down. You can pick which level you pick the wave at. And so it could be at the solar system level that you can use
it. And also it actually provides a pretty neat calculational tool, because It's difficult. So we just talked about simulations, but it's difficult to simulate the behavior of astrophysical disks on timescales that are in between a few orbits and their entire evolution. So it's over a timescale of a few orbits. You do a hydrodynamic, simulation, right? You do that. Basically, that's something that you can do on a modern computer on a timescale of, say, a week. When it comes to their evolution over their entire lifetime, you don't hope to resolve the orbits. You just kind of hope to understand how the system behaves. In between, right? To get access to that, as it turns out, it's pretty cute. You can use the Schrodinger equation to get the answer rapidly. So it's a calculational
underpinning it.
Can we dig into that process of starting from one place and then ending up at like the fourth step and realizing all along that the place you started at was wrong? So is that happen when there's a discrepancy between what the math says and what the physical world shows? Is that how you then can go back and do the revolutionary idea for different starting place altogether?
Perhaps I'll give an example to see how it goes. And in fact, the historical example is Newton's work on classical mechanics. So Newton formulated the laws of mechanics, the force F equals to ma and his other laws, and they look very simple, elegant, and so forth. Later, when we studied more examples of mechanics and other similar things, physicists came up with the idea that the notion of potential is interesting. Potential was an abstract idea which kind of came, you could take its gradient and relate it to the force, so you don't really need it a priori, but it helped some thoughts. And then later, Euler and Lagrange reformulated Newtonian mechanics in a totally different way in the following fashion. They said, if you want to know where a particle at this point and at this time, how does it get to this point at the later time, is the following. You take all possible paths connecting this particle from going from the initial point to the final point, and you compute the action. And what is an action? Action is the integral over time of the kinetic term of the particle minus its potential. So you take this integral, and each path will give you some quantity. And the path it actually takes, the physical path, is the one which minimizes this integral or this action. Now, this sounded like a backward step from Newton's. Newton's formula seemed very simple. F equals to ma, and you can write F is minus the gradient of the potential. So why would anybody start formulating such a simple thing in terms of this complicated looking principle? You have to study the space of all paths and all things and find the minimum, and then you get the same equation. So what's the point? So Euler and Lagrange's formulation of Newton, which was kind of a recasting in this language, is just a consequence of Newton's law. F equals to ma gives you the same fact that this path is a minimum action. Now, what we learned later, last century, was that when we deal with quantum mechanics, Newton's law is only an average correct. And the particle going from one to the other doesn't take exactly one path. It takes all the paths.
Yes.
With the amplitude, which is proportional to the exponential of the action times an imaginary number, I. And so this fact turned out to be the reformulation of quantum mechanics. We should start there as the basis of the new law, which is quantum mechanics. And Newton is only an approximation and the average correct.
When we say amplitude, you mean probability?
But yes, the amplitude means that if you sum up all these paths with the exponential I times the action, if you sum this up, you get the number, complex number. You square the norm of this complex number, gives you a probability to go from one to.
Where does quantum mechanics come into view?
Exactly. So this is the next step. So Einstein's, developed general relativity, and he's beginning to develop the foundation of quantum mechanics at the same time, the photoelectric effects and others. And so quantum mechanics overtakes, in fact, Einstein in many ways because he doesn't like the probabilistic interpretation of quantum mechanics and the formalism that's emerging. But physicists march on and try to, for example, combine Einstein's theory of relativity with quantum mechanics. So Dirac takes special relativity, tries to see how is it compatible with quantum mechanics.
Can we pause and briefly say what is quantum mechanics?
Oh, yes, sure. So quantum mechanics, so I discussed briefly when I talked about the connection between Newtonian mechanics and the Euler-Lagrange reformulation of the Newtonian mechanics and interpretation of this Euler-Lagrange formalism in terms of the paths that the particle take. So when we say a particle goes from here to here, we usually think it classically it follows a specific trajectory, but actually in quantum mechanics, it follows every trajectory with different probabilities. And so there's this fuzziness. Now, most probable, it's the path that you actually see. And the deviation from that is very, very unlikely and probabilistically very minuscule. So in everyday experiment, we don't see anything deviated from what we expect. But quantum mechanics tells us that things are more fuzzy. Things are not as precise as the line you draw. Things are a bit like cloud. So if you go to microscopic scales, like atomic scales and lower, these phenomena become more pronounced. You can see it much better. The electron is not at the point, but the cloud spread out around the nucleus. And so this fuzziness, this probabilistic aspect of reality is what quantum mechanics describes.
Can I briefly pause on that idea? Do you think this is quantum mechanics is just a really damn good approximation, a tool for predicting reality, or does it actually describe reality? Do you think reality is fuzzy at that level?
Well, I think that reality is fuzzy at that level, but I don't think quantum mechanics is necessarily the end of the story.
Right.
So, so quantum mechanics is certainly an improvement over classical physics. That much we know by experiments and so forth. Whether I'm happy with quantum mechanics, whether I view quantum mechanics, for example, the measurement description of quantum mechanics, am I happy with it? Am I thinking that's the end stage or not? I don't think we're at the end of that story, and many physicists may or may not view this way. Some do, some don't. But I think that it's the best we have right now, that's for sure. It's the best approximation for reality we know today. And so far, we don't know what it is, the next thing that improves it or replaces it and so on. So, but as I mentioned before, I don't believe any of the laws of physics we know today are permanently exactly correct. And it doesn't bother me.
Yes.
I'm not like dogmatic saying, I have figured out this is the law of nature. I know everything. No, that's the beauty about science, that we are not dogmatic. And we are willing to, in fact, we are encouraged to be skeptical of what we ourselves do.
So you were talking about Dirac.
Yes, I was talking about Dirac, right? So Dirac was trying to now combine this Schrodinger's equations, which was described in the context of, trying to talk about how these probabilistic waves of electrons move for the atom, which was good for speeds which were not too close to the speed of light, to what happens when you get to near the speed of light. So then you need relativity. So then Dirac tried to combine Einstein's relativity with quantum mechanics. So he tried to combine them, and he wrote this beautiful equation, the Dirac equation, which, roughly speaking, take the square root of the Einstein's equation in order to connect it to Schrodinger's time evolution operator, which is first order in time derivative, to get rid of the naive thing that Einstein's equation would have given, which is second order. So you have to take a square root. Now, square root usually has a plus or minus sign when you take it. And when he did this, he originally didn't notice this, didn't pay attention to this plus or minus sign, but later physicists pointed out to Dirac, says, look, there's also this minus sign, and if you use this minus sign, you get negative energy. In fact, it was very, very annoying that, somebody else tells you this obvious mistake you make. Pauli, famous physicist, told Dirac, this is nonsense. You're going to get negative energy with your equation, which negative energy without any bottom. You can go all the way down to negative infinite energy. So it doesn't make any sense. Dirac thought about it, and then he remembered Pauli's exclusion principle. Just before him, Pauli had said, there's this principle called the exclusion principle that, two electrons cannot be on the same orbit. Mm-hmm. And so Dirac said, okay, you know what? All these negative energy states are filled orbits. Occupied. So according to you, Mr. Pauli, there's no place to go. So therefore they only have to go positive. Sounded like a big cheat. And then Pauli said, oh, you know what? We can change orbits from one orbit to another. What if I take one of these negative energy orbits and put it up there? Then it seems to be a new particle, which has opposite properties to the electron. It has positive energy, but it has positive charge. What is that? Dirac was a bit worried. He said, maybe that's proton, because proton has plus charge. He wasn't sure. But then he said, oh, maybe it's proton. But then they said, no. It has the same mass as the electron. It cannot be proton because proton is heavier. Dirac was stuck. He says, well, then maybe another particle we haven't seen. By that time, Dirac himself was getting a little bit worried about his own equation and his own crazy interpretation.
Yes.
Until a few years later, Anderson, in the photographic plates that he had gotten from these cosmic rays, he discovered a particle which goes in the opposite direction that the electron goes when there's a magnetic field, and with the same mass, exactly like what Dirac had predicted. And this was what we call now positron. And in fact, beginning with the work of Dirac, we know that every particle has an antiparticle. And so this idea that there's an antiparticle came from this simple math, there's a plus and a minus from the Dirac's quote-unquote mistake. So again, trying to combine ideas, sometimes the math is smarter than the person who uses it to apply it, and you try to resist it, and then you kind of confront it by criticism, which is the way it should be. So physicist comes and says, no, that's wrong, and you correct it and so on. So that is a development of the idea there's particle, there's antiparticle, and so on. So this is the beginning of development of quantum mechanics and the connection with relativity. But the thing was more challenging because we had to also describe how electric and magnetic fields work with quantum mechanics. Mm-hmm. This was much more complicated because it's not just one point. Electric and magnetic fields were everywhere. So you had to talk about fluctuating and a fuzziness of electrical field and magnetic fields everywhere. And the math for that was very difficult to deal with. And this led to a subject called quantum field theory. Fields like electric and magnetic fields had to be quantum, had to be described also in a wavy way. Feynman, in particular, was one of the pioneers, and along with Schwingers and others, to try to come up with a formalism to deal with fields like electric and magnetic fields interacting with electrons in a consistent quantum fashion. And they developed this beautiful theory, quantum electrodynamics, from that. And later on, that same formalism, quantum field theory, led to the discovery of other forces and other particles, all consistent with the idea of quantum mechanics. So that was how physics progressed. And so basically we learned that all particles and all the forces are in some sense related to particle exchanges. And so, for example, electromagnetic forces are mediated by a particle we call photon, mm-hmm. and so forth. And the same for other forces that they discovered, strong forces and the weak forces. So we got the sense of what quantum field theory is.
Is that a big leap of an idea that particles are fluctuations in a field? Like the idea that everything is a field? Is the old Einstein light is a wave, both a particle and a wave kind of idea? Is that a huge leap in our understanding of conceiving the universe as fields?
I would say so. I would say that viewing the particles, this duality that Bohr mentioned between particles and waves, that waves can behave sometimes like particles, sometimes like waves, is one of the biggest leaps of imagination that quantum mechanics made physicists do. So I agree that is quite remarkable.
Is duality fundamental to the universe, or is it just because we don't understand it fully? Like, will it eventually collapse into a clean explanation that doesn't require duality? Like, that a phenomena could be two things at once and both to be true. So that seems weird.
So in fact, I was going to get to that when we get to string theory, but maybe I can comment on that now. Duality turns out to be running the show today in the whole thing that we are doing in string theory. Duality is the name of the game. So it's the most beautiful subject, and I want to talk about it.
Let's talk about it in the context of string theory.
Let's talk about the context of string theory.
So we do we want to take a next step into, because we mentioned general relativity, we mentioned quantum mechanics. Is there something to be said about quantum gravity?
Yes, that's exactly the right point to talk about. So namely, we have talked about quantum fields, and I talked about electric forces, photon being the particle carrying those forces. So for gravity, quantizing gravitational field, which is this curvature of space-time according to Einstein, you get another particle called graviton. So what about gravitons? Should be there, no problem. So then you start computing it. What do I mean by computing it? Well, you compute scattering of one graviton off another graviton, maybe with graviton with an electron, and so on, see what you get. Feynman had already mastered this quantum electrodynamics. He said, no problem, let me do it. even though these are such weak forces, the gravity is very weak. So therefore, to see them, these quantum effects of gravitational waves was impossible. It's even impossible today. So Feynman just did it for fun. He usually, had this mindset that I want to do something which I will see in experiment, but this one, let's just see what it does. And he was surprised because the same techniques he was using for doing the same calculations, quantum electrodynamics, when applied to gravity, failed. The formulas seemed to make sense, but he had to do some integrals, and he found that when he does those integrals, he got infinity. And it didn't make any sense. Now, there were similar infinities in the other pieces, but he had managed to make sense out of those before. This was no way he could make sense out of it. He just didn't know what to do. He didn't feel it's an urgent issue because nobody could do the experiment. So he was kind of said, okay, there's this thing, but okay, we don't know how to exactly do it, but that's the way it is. So in some sense, a natural conclusion from what Feynman did could have been like, gravity cannot be consistent with quantum theory. But that cannot be the case because gravity is in our universe, quantum mechanics is in our universe, they both together somehow should work. So it's not acceptable to say they don't work together. So that was a puzzle. How does it possibly work? It was left open. And then we get to the string theory. So this is the puzzle of quantum gravity. The particle description of quantum gravity failed.
So the infinity shows up. What do we do? What do we do with it? What is quantum mechanics?
Quantum mechanics is the paradigm of physics that came into being in the early part of the 20th century that replaced classical mechanics. And it replaced classical mechanics in a weird way that we're still coming to terms with. So in classical mechanics, you have an object, it has a location, it has a velocity, and if you know the location and velocity of everything in the world, you can say what everything's going to do. Quantum mechanics has an aspect of it that is kind of on the same lines. There's something called the quantum state or the wave function. And there's an equation governing what the quantum state does. So it's very much like classical mechanics. The wave function is different. It's sort of a wave. It's a vector in a huge dimensional vector space rather than a position and a velocity. But okay, that's a detail. And the equation is the Schrödinger equation, not Newton's laws, but okay, again, a detail. Where quantum mechanics really becomes weird and different is that there's a whole nother set of rules in our textbook formulation of quantum mechanics, in addition to saying that there's a quantum state and it evolves in time. And all these new rules have to do with what happens when you look at the system, when you observe it, when you measure it. In classical mechanics, there were no rules about observing. You just look at it and you see what's going on. That was it, right? In quantum mechanics, the way we teach it, there's something profoundly fundamental about the act of measurement or observation, and the system dramatically changes its state. Even though it has a wave function, like the electron in an atom is not orbiting in a circle, it's sort of spread out in a cloud. When you look at it, you don't see that cloud. When you look at it, it looks like a particle with a location. So it dramatically changes its state right away. And the effects of that change can be instantly seen in what the electron does next. So that's again, we need to be careful because we don't agree on what quantum mechanics says. So that's why I need to say, like, in the textbook view, et cetera, right? But in the textbook view, quantum mechanics, unlike any other theory of physics, gives a fundamental role to the act of measurement.
So maybe even more basic. Is there anything that quantum mechanics can teach us about human nature or the human mind? Do you think about sort of consciousness and these kinds of topics? It's certainly excessively used, as you point out. The word quantum is used for everything besides quantum mechanics. But in more seriousness, is there something that goes to the human level and can help us understand our mind?
Not really is the short answer. Minds are pretty classical. I don't think, we don't know this for sure, but I don't think that phenomena like entanglement are crucial to how the human mind works.
What about consciousness? So you mentioned, I think early on in the conversation, you said it would be unlikely but incredible if sort of the observer is somehow a fundamental part. So if observer, not to romanticize the notion, but seems interlinked to the idea of consciousness. So if consciousness is, as the panpsychists believe, is fundamental to the universe, Is that possible? Is that
Everything's possible.
just like Joe Rogan likes to say, it's entirely possible.
Right.
But is it on a spectrum of crazy out there? How like statistically speaking, how often do you ponder the possibility that consciousness is fundamental or the observer is fundamental to?
I personally don't at all. There are people who do. I'm a thorough physicalist when it comes to consciousness. I do not think that there are any separate mental states or mental properties. I think they're all emergent, just like spacetime is. And, spacetime is hard enough to understand. So the fact that we don't yet understand consciousness is not at all surprising to me.
So coming back to the textbook definition of quantum mechanics, this idea that I don't think we talked about, one of the most interesting philosophical points, we talked at the human level, but at the physics level, that at least the textbook definition of quantum mechanics separates what is observed and what is real. How does that make you feel? And two, what does it then mean to observe something, and why is it different than what is real?
Yeah, my personal feeling, such as it is that things like measurement and observers and stuff like that are not going to play a fundamental role in the ultimate laws of physics. But my feeling that way is because so far that's where all the evidence has been pointing. I could be wrong, and there's certainly a sense in which it would be infinitely cool if somehow observation or mental cogitation did play a fundamental role in the nature of reality. But I don't think so. And again, I don't see any evidence for it. So I'm not spending a lot of time worrying about that possibility. So what do you do about the fact that in the textbook interpretation of quantum mechanics, this idea of measurement or looking at things seems to play an important role? Well, you come up with better interpretations of quantum mechanics, and there are several alternatives. My favorite is the many worlds interpretation, which says two things. Number one, you, the observer, are just a quantum system like anything else. There's nothing special about you. Don't get so proud of yourself. You're just a bunch of atoms. You have a wave function. You obey the Schrodinger equation like everything else. And number two, when you think you're measuring something or observing something, what's really happening is you're becoming entangled with that thing. So when you think that there's a wave function for the electron, it's all spread out, but you look at it and you only see it in one location. What's really happening is that there's still the wave function for the electron in all those locations, but now it's entangled with the wave function of you in the following way. There's part of the wave function that says the electron was here and you think you saw it there. The electron was there and you think you saw it there. The electron was over there and you think you saw it there, etc. So, and all of those different parts of the wave function, once they come into being, no longer talk to each other. They no longer interact or influence each other. It's as if they are separate worlds. So this was the invention of Hugh Everett III, who was a graduate student at Princeton in the 1950s. And he said, basically, look, you don't need all these extra rules about looking at things. Just listen to what the Schrodinger equation is telling you. It's telling you that you have a wave function, that you become entangled, and that the different versions of you no longer talk to each other. So just accept it. It's just, he did therapy more than anything else. He said, it's okay. You don't need all these extra rules. All you need to do is believe the Schrodinger equation. The cost is there's a whole bunch of extra worlds out there.
So the world's being created, whether there's an observer or not.
The worlds are created anytime a quantum system that's in a superposition becomes entangled with the outside world.
What's the outside world?
It depends. Let's back up.
Yep.
Whatever it really says, what his theory is there's a wave function of the universe and it obeys the Schrodinger equation all the time. That's it. That's the full theory right there, okay? The question, all of the work, is how in the world do you map that theory onto reality, onto what we observe, right? So part of it is carving up the wave function into these separate worlds, saying, look, it describes a whole bunch of things that don't interact with each other. Let's call them separate worlds. Another part is distinguishing between systems and their environments. And the environment is basically all the degrees of freedom, all the things going on in the world that you don't keep track of. So again, in the bottle of water, I might keep track of the total amount of water and the volume. I don't keep track of the individual positions and velocities. I don't keep track of all the photons or the air molecules in this room. So that's the outside world. The outside world is all the parts of the universe that you're not keeping track of when you're asking about the behavior of subsystem of it.
So how many worlds are there?
Yeah, we don't know that one either. There could be an infinite number. There could be only a finite number, but it's a big number one way or the other.
So it's a very, very big number. In one of the talks, somebody asked, well, if it's finite, so actually, I'm not sure exactly the logic you used to derive this, but is there, going to be, overlap, a duplicate world that you return to? So you've mentioned, and I'd love if you can elaborate on sort of idea that it's possible that there's some kind of equilibrium that these splitting worlds arrive at, and then maybe over time, maybe somehow connected to entropy, you get a large number of worlds that are very similar to each other.
Yeah, so this question of whether or not Hilbert space is finite or infinite dimensional is actually secretly connected to gravity and cosmology. This is the part that we're still struggling to understand right now. But we discovered back in 1998 that our universe is accelerating. And what that means, if it continues, which we think it probably will, but we're not sure. But if it does, that means there's a horizon around us. Because the universe is not only expanding, but expanding faster and faster, things can get so far away from us that from our perspective, it looks like they're moving away faster than the speed of light. We will never see them again. So there's literally a horizon around us, and that horizon approaches some fixed distance away from us. And you can then argue that within that horizon, there's only a finite number of things that can possibly happen, the finite dimensional Hilbert space. In fact, we even have a guess for what the dimensionality is. It's 10 to the power of 122. That's a very large number.
Yes.
Just to compare, the age of the universe is something like 10 to the 14 seconds. 10 to the 17 or 18 seconds, maybe. The number of particles in the universe is 10 to the 88th, but the number of dimensions of Hilbert space is 10 to the 122. So that's just crazy big. If that story is right, that in our observable horizon, there's only a finite dimensional Hilbert space, then this idea of branching of the wave function of the universe into multiple distinct separate branches has to reach a limit at some time. Once you branch that many times, you run out of room in Hilbert space. And roughly speaking, that corresponds to the universe just expanding and emptying out and cooling off and entering a phase where it's just empty space literally forever.
What's the difference between splitting and copying, do you think? Like in terms of, a lot of this is an interpretation that helps us sort of model the world. So perhaps shouldn't be thought of as like, philosophically or metaphysically, but even at the physics level, do you see a difference between sort of generating new copies of the world or splitting?
I think it's better to think of, in quantum mechanics, in many worlds, the universe splits rather than new copies, because people otherwise worry about things like energy conservation. Right. And no one who understands quantum mechanics worries about energy conservation because the equation is perfectly clear. But if all you know is that someone told you the universe duplicates, then you have a reasonable worry about where all the energy for that came from. So a pre-existing universe splitting into two skinnier universes is a better way of thinking about it. And mathematically, it's just like, if you draw an x and y axis and you draw a vector of length 1 at 45-degree angle, you know that you can write that vector of length 1 as the sum of two vectors pointing along x and y of length 1 over the square root of 2. Okay? So I write one arrow as the sum of two arrows. But there's a conservation of arrowness, right? Like there's now two arrows, but the length is the same. I'm describing it in a different way. And that's exactly what happens when the universe branches. The wave function of the universe is a big old vector.
So to somebody who brings up a question of saying, doesn't this violate the conservation of energy? Can you give a further elaboration?
Right. So let's just be super duper perfectly clear.
Yeah.
There's zero question about whether or not many worlds violates conservation of energy.
Yes.
It does not.
Great.
And I say this definitively because there are other questions that I think there's answers to, but they're legitimate questions, right? About, where does probability come from and things like that. This conservation of energy question, we know the answer to it, and the answer to it is that energy is conserved.
Yes.
All of the effort goes into how best to translate what the equation unambiguously says into plain English, right?
Right.
So this idea that there's a universe that has that the universe comes equipped with a thickness and it sort of divides up into thinner pieces, but the total amount of universe is conserved over time is a reasonably good way of putting English words to the underlying mathematics.
So one of my favorite things about many worlds is, I love that there's something controversial in science. And for some reason, it makes people actually not like upset, but just get excited. Why do you think it is a controversial idea? So there's a lot of, it's actually one of the cleanest ways to think about quantum mechanics.
Yeah.
So why do you think there's a discomfort a little bit among certain people?
Well, I draw the distinction in my book between two different kinds of simplicity in a physical theory. There's simplicity in the theory itself, right? How we describe what's going on according to the theory by its own rights. But then, a theory is just some sort of abstract mathematical formalism. You have to map it onto the world somehow, right? And sometimes, like for Newtonian physics, it's pretty obvious. Like, okay, here is a bottle and it has a center of mass and things like that. Sometimes it's a little bit harder. With general relativity, curvature of space-time is a little bit harder to grasp. Quantum mechanics is very hard to map the language you're talking in of wave functions and things like that onto reality. And many worlds is the version of quantum mechanics where it is hardest to map on the underlying formalism to reality. So that's where the lack of simplicity comes in, not in the theory, but in how we use the theory to map onto reality. And in fact, all of the work in sort of elaborating many worlds quantum mechanics is in this effort to map it on to the world that we see. So it's perfectly legitimate to be bugged by that, right? To say like, well, no, that's just too far away from my experience. I am therefore intrinsically skeptical of it. Of course, you should give up on that skepticism if there are no alternatives and this theory always keeps working, then eventually you should overcome your skepticism. But right now there are alternatives that people work to make alternatives that are by their nature closer to what we observe directly.
Can you describe the alternatives? I don't think we touched on it. Sort of the Copenhagen interpretation and the many worlds. Maybe there's a difference between the Everettian many worlds and many worlds as it is now. Like has the idea sort of developed and so on. And just in general, what is the space of promising contenders? We have democratic debates now. There's a bunch of candidates.
12 candidates
on stage. What are the quantum mechanical candidates on stage for the debate?
So if you had a debate between quantum mechanical contenders, there would be no problem getting 12 people up there on stage, but there would still be only 3 frontrunners. Yes. And right now the frontrunners would be Everett. Hidden variable theories are another one. So the hidden variable theories say that the wave function is real, but there's something in addition to the wave function. The wave function is not everything. It's part of reality, but it's not everything. What else is there? We're not sure. But in the simplest version of the theory, they're literally particles. So many worlds says that quantum systems are wave-like in some ways and particle-like in another because they really, really are waves. But under certain observational circumstances, they look like particles. Whereas hidden variable says they look like waves and particles because there are both waves and particles involved in the dynamics. And that's easy to do if your particles are just non-relativistic Newtonian particles moving around. They get pushed around by the wave function roughly. It becomes much harder when you take quantum field theory or quantum gravity into account. The other big contender are spontaneous collapse theories. So in the conventional textbook interpretation, we say when you look at a quantum system, its wave function collapses and you see it in one location. A spontaneous collapse theory says that every particle has a chance per second of having its wave function spontaneously collapse. The chance is very small. For a typical particle, it will take hundreds of millions of years before it happens even once. But in a table or some macroscopic object, there are way more than 100 million particles, and they're all entangled with each other. So when one of them collapses, it brings everything else along with it. There's a slight variation of this. That's a spontaneous collapse theory. There are also induced collapse theories, like Roger Penrose thinks that when the gravitational difference between two parts of the wave function becomes too large, the wave function collapses automatically. So those are basically, in my mind, the three big alternatives. Many worlds, which is just there's a wave function, it always obeys the Schrodinger equation. Hidden variables, there's a wave function that always obeys the Schrodinger equation, but there are also new variables. Or collapse theories, which the wave function sometimes obeys the Schrodinger equation and sometimes it collapses. So you can see that the alternatives are more complicated in their formalism than many worlds is, but they are closer to our experience.
So just this moment of collapse, do you think of it as, so is a wave function fundamentally sort of a probabilistic description of the world? And is collapse sort of reducing that part of the world into something deterministic, where again you can now describe the position and the velocity in this simple classical model?
Well,
is that how you think about collapse?
There is a fourth category, there's a fourth contender. There's a Mayor Pete of quantum mechanical interpretations, which are called epistemic interpretations. And what they say is all the wave function is a way of making predictions for experimental outcomes. It's not mapping onto an element of reality in any real sense. And in fact, two different people might have two different wave functions for the same physical system because they know different things about it, right? The wave function is really just a prediction mechanism. And then the problem with those epistemic interpretations is if you say, okay, but it's predicting about what? Like, what is the thing that is being predicted? And they say, no. That's not what we're here for. We're just here to tell you what the observational outcomes are going to be.
But the other interpretations kind of think that the wave function is real.
Yes, that's right. So that's an ontic interpretation of the wave function, ontology being the study of what is real, what exists, as opposed to an epistemic interpretation of the wave function, epistemology being the study of what we know.
I would actually just love to see that debate on stage.
There was a version of it on stage at the World Science Festival a few years ago that you can look up online.
And on YouTube?
Yep, it's on YouTube.
Okay, awesome. I'll link it and watch it.
Many worlds.
Who won?
I won. No, I don't know. There was no vote. There was no vote. But there's Brian Greene was the moderator, and David Albert stood up for spontaneous collapse, and Shelley Goldstein was there for hidden variables, and Rudiger Schock was there for epistemic approaches.
Why do you? I think you mentioned it, but just to elaborate, why do you find many worlds so compelling?
Well, there's two reasons, actually. One is, like I said, it is the simplest, right? It's like the most bare bones, austere, pure version of quantum mechanics. And I am someone who is very willing to put a lot of work into mapping the formalism onto reality. I'm less willing to complicate the formalism itself. But the other big reason is that there's something called modern physics with quantum fields and quantum gravity and holography and spacetime, doing things like that. And when you take any of the other versions of quantum theory, they bring along classical baggage. All of the other versions of quantum mechanics prejudice or privilege some version of classical reality like locations in space, okay? And I think that that's a barrier to doing better at understanding the theory of everything and understanding quantum gravity and the emergence of space-time. If you change your theory from, here's a harmonic oscillator, there's a spin, here's an electromagnetic field. In hidden variable theories or dynamical collapse theories, you have to start from scratch. You have to say, what are the hidden variables for this theory, or how does it collapse, or whatever. Whereas many worlds is plug and play. You tell me the theory and I can give you its many worlds version. So when we have a situation like we have with gravity and space-time, where the classical description seems to break down in a dramatic way, then I think you should start from the most quantum theory that you have, which is really many worlds.
So start with the quantum theory and try to build up a model. Can you say what is entanglement? it seems one of the most fundamental ideas of quantum mechanics.
Well, let's temporarily buy into the textbook interpretation of quantum mechanics. And what that says is that this wave function, so it's very small outside the atom, very big in the atom. Basically, the wave function, you take it and you square it. You square the number. That gives you the probability of observing the system at that location. So if you say that for 2 electrons, there's only one wave function, and that wave function gives you the probability of observing both electrons at once doing something, okay? So maybe the electron can be here or here or here or here, and the other electron can also be there, but we have a wave function set up where we don't know where either electron is going to be seen, but we know they'll both be seen in the same place, okay? So we don't know exactly what we're going to see for either electron, but there's entanglement between the two of them. There's a sort of conditional statement. If we see one in one location, then we know the other one's going to be doing a certain thing. So that's a feature of quantum mechanics that is nowhere to be found in classical mechanics. In classical mechanics, there's no way I can say, well, I don't know where either one of these particles is, but if I find out where this one is, then I know where the other one is. That just never happens. They're truly separate.
And in general, it feels like if you think of a wave function like as a dance floor, it seems like entanglement is strongest between things that are dancing together closest. So there's a closeness that's important.
Well, that's another step. We have to be careful here, sure. Because in principle, if you're talking about the entanglement of 2 electrons, for example, they can be totally entangled or totally unentangled no matter where they are in the universe. There's no relationship between the amount of entanglement and the distance between 2 electrons. But we now know that, the reality of our best way of understanding the world is through quantum fields, not through particles. So even the electron, not just gravity and electromagnetism, but even the electron and the quarks and so forth are really vibrations in quantum fields. So even empty space is full of vibrating quantum fields. And those quantum fields in empty space are entangled with each other in exactly the way you just said. If they're nearby, if you have like 2 vibrating quantum fields that are nearby, then they will be highly entangled. If they're far away, they will not be entangled.
So what do quantum fields in a vacuum look like? Empty space?
Just looks like empty space. It's as empty as it can be.
But there's still a field. It's just... Yeah. What does nothing
just like right here, this location in space, there's a gravitational field, which I can detect by dropping something, right? I don't see it, but there it is.
So we got a little bit of a idea of entanglement. Now, quantum computers. There's some excitement, actually a lot of excitement with people that it will allow us to simulate quantum mechanical systems. What kind of questions about quantum mechanics, about the things we've been talking about, do you hope we can answer through quantum simulation?
Well, I think that there's a whole fascinating frontier of things you can do with quantum computers, both sort of practical things with cryptography or money, privacy eavesdropping, sorting things, simulating quantum systems, right?
So it's a broader question. So what do you think Newton would say, maybe write in a book review if you read your latest book on quantum mechanics, Something Deeply Hidden?
It would take a long time for him to think that any of this was making any sense.
You catch him up pretty quick in the beginning.
Yeah.
you give him a shout out in the beginning.
That's right. I mean, he was the man. I'm happy to say that Newton was the greatest scientist who ever lived. He invented calculus in his spare time, which would have made him the greatest mathematician just all by himself, right? All by that one thing. But of course, it's funny because Newton was in some sense still a pre-modern thinker. Rocky Kolb, who was a cosmologist at the University of Chicago, said that, Galileo, even though he came before Newton, was a more modern thinker than Newton was. Like if you got Galileo and brought him to the present day, it'd take him 6 months to catch up, and then he'd be in your office telling you why your most recent paper was wrong. Whereas Newton just thought in this kind of more mystical way. He wrote a lot more about the Bible and alchemy than he ever did about physics. But he was also more brilliant than anybody else and way more mathematically astute than Galileo. So I really don't know. He might just say, like, give me the textbooks, leave me alone for a few months and then be caught up. Or he might have had mental blocks against seeing the world in this way. I really don't know.
Or perhaps find an interesting mystical interpretation of quantum mechanics.
Very possible, yeah.
Is there any other scientists or philosophers through history that you would like to know their opinion of your book?
That's a good question. Einstein is the obvious one, right? He was not that long ago, but I even speculate at the end of my book about what his opinion would be. Yeah. I am curious as to, what about older philosophers like Hume or Kant, right? Like, what would they have thought, or Aristotle? What would they have thought about modern physics? Because they do, in philosophy, your predilections end up playing a much bigger role in your ultimate conclusions because you're not as tied down by what the data is. In physics, physics is lucky because we can't stray too far off the reservation as long as we're trying to explain the world that we actually see in our telescopes and microscopes. But it's just not fair to play that game because the people we're thinking about didn't know a whole bunch of things that we know, right? Like we lived through a lot that they didn't live through. So by the time we got them caught up, they'd be different people.
So let me ask a bunch of basic questions. I think it would be interesting, useful for people who are not familiar, but even for people who are extremely well familiar. Let's start with spacetime. The emergence of spacetime.
That's right.
Okay, so I thought spacetime was fundamental.
Yeah, I know.
So this sort of dream that Einstein had, that everybody had and everybody has, of, the theory of everything. So how do we build up from many worlds, from quantum mechanics, a model of space-time, model of gravity?
Well, yeah, let me first mention very quickly why we think it's necessary. We've had gravity in the form that Einstein bequeathed it to us for over 100 years now. Like 1915 or 1916, he put general relativity in the final form. So gravity is the curvature of space-time, and there's a field that pervades all the universe that tells us how curved space-time is.
And that's a fundamentally classical...
That's totally classical, right? Exactly. But we also have a formalism, an algorithm for taking a classical theory and quantizing it. This is how we get quantum electrodynamics, for example. And it could be tricky. You think you're quantizing something, so that means taking a classical theory and promoting it to a quantum mechanical theory. But you can run into problems. So they ran into problems when they did that with electromagnetism, namely that certain quantities were infinity, and you don't like infinity, right? Nope. So Feynman and Tominaga and Schwinger won the Nobel Prize for teaching us how to deal with the infinities. And then Ken Wilson won another Nobel Prize for saying you shouldn't have been worried about those infinities after all. But still, it's always the thought that that's how you will make a good quantum theory. You'll start with a classical theory and quantize it. So if we have a classical theory, general relativity, we can quantize it, or we can try to, but we run into even bigger problems with gravity than we ran into with electromagnetism. And so far, those problems are insurmountable. We've not been able to get a successful theory of gravity, quantum gravity, by starting with classical general relativity and quantizing it. And there's evidence that there's a good reason why this is true, that whatever the quantum theory of gravity is, it's not a field theory. It's something that has weird non-local features built into it somehow that we don't understand. And we get this idea from black holes and Hawking radiation and information conservation and a whole bunch of other ideas I talk about in the book. So if that's true, if the fundamental theory isn't even local in the sense that an ordinary quantum field theory would be, then we just don't know where to start in terms of getting a classical precursor and quantizing it. Right. So the only sensible thing, at least the next obvious sensible thing to me, would be to say, okay, let's just start intrinsically quantum and work backwards, see if we can find a classical limit.
So the idea of locality, the fact that locality is not fundamental to the nature of our existence, I guess in that sense, modeling everything as a field makes sense to me. Stuff that's close by interacts, stuff that's far away doesn't. So what's locality and why is it not fundamental? And how is that even possible?
Yeah, locality is the answer to the question that Isaac Newton was worried about back at the beginning of our conversation, right? How can the Earth know what the gravitational field of the sun is? And the answer, as spelled out by Laplace and Einstein and others, is that there's a field in between. And the way a field works is that what's happening to the field at this point in space only depends directly on what's happening at points right next to it. But what's happening at those points depends on what's happening right next to those, right? And so you can build up an influence across space through only local interactions. That's what locality means. What happens here is only affected by what's happening right next to it. That's locality. The idea of locality is built into every field theory, including general relativity as a classical theory. It seems to break down when we talk about black holes. And, Hawking taught us in the 1970s that black holes radiate. They give off, they will eventually evaporate away. They're not completely black once we take quantum mechanics into account. And we don't know for sure, but most of us think that if you make a black hole out of certain stuff, then like Laplace's demon taught us, you should be able to predict what that black hole will turn into if it's just obeying the Schrodinger equation. And if that's true, there are good arguments that can't happen while preserving locality at the same time. It's just that the information seems to be spread out non-locally in interesting ways.
And people should, you talk about holography with Leonard Susskind on your Mindscape podcast. People should
yes, I have a podcast. I didn't even mention that. I'm terrible at
No, I'm gonna ask you questions about that too. And
okay.
I've been not shutting up about it. It's my favorite science podcast. It's not even a science podcast. It's like it's a scientist doing a podcast.
That's right. That's what it is. Absolutely, yes.
Yeah. Okay. Anyway,
so holography is this idea when you have a black hole, and black hole is a region of space inside of which gravity is so strong that you can't escape. And there's this weird feature of black holes that, again, is totally a thought experiment feature because we haven't gone and probed any yet. But there seems to be one way of thinking about what happens inside a black hole as seen by an observer who's falling in, which is actually pretty normal. Like everything looks pretty normal until you hit the singularity and you die. But from the point of view of the outside observer, it seems like all the information that fell in is actually smeared over the horizon in a non-local way. And that's puzzling. And that's so holography, because that's a two-dimensional surface that is encapsulating the whole three-dimensional thing inside, right? Still trying to deal with that, still trying to figure out how to get there. But it's an indication that we need to think a little bit more subtly when we quantize gravity.
So because you can describe everything that's going on in in three-dimensional space by looking at the two-dimensional projection of it, means that locality is not necessary.
Well, it means it's only a good approximation. It's not really what's going on.
How are we supposed to feel about that?
We're supposed to feel liberated. Space is just a good approximation. And this was always going to be true once you started quantizing gravity. So we're just beginning now to face up to the dramatic implications of quantizing gravity.
Is there other weird stuff that happens to quantum mechanics in a black hole?
I don't think that anything weird has happened with quantum mechanics. I think weird things happen with space-time. I mean, that's what it is. Like quantum mechanics is still just quantum mechanics, but our ordinary notions of space-time don't really quite work. And there's a principle that goes hand in hand with holography called complementarity, which says that there's no one unique way to describe what's going on inside a black hole. Different observers will have different descriptions, both of which are accurate, but sound completely incompatible with each other. So it depends on how you look at it. The word complementarity in this context is borrowed from Niels Bohr, who points out you can measure the position or you can measure the momentum. You can't measure both at the same time in quantum mechanics.
So a couple of questions on many world.
Personally.
So that's P and NP, but the complexity zoo is full of wonderful creatures.
Well, it's got about 500 of them.
500. So how do you get more? How do you get more? How do you,
I mean, just for starters, there is everything that we could do with a conventional computer with a polynomial amount of memory. Okay, but possibly an exponential amount of time because we get to reuse the same memory over and over again. Okay, that is called P space. Mm-hmm. Okay, and that's actually we think an even larger class than NP. Okay, well, P is contained in NP, which is contained in P space, and we think that those containments are strict.
And the constraint there is on the memory. The memory has to grow polynomially with the size of the problem.
That's right. But in P space, we now have interesting things that were not in NP, as a famous example, from a given position in chess, does white or black have the win? Let's say, assuming provided that the game lasts only for a reasonable number of moves.
Oh,
okay,
interesting.
or likewise for Go. Okay, and even for the generalizations of these games to arbitrary size boards. Because with an 8x8 board, you could say that's just a constant size problem. You just, in principle, you just solve it in O of one time, right? Yeah. But so we really mean the generalizations of games to arbitrary size boards here. Or another thing in p-space would be I give you some really hard constraint satisfaction problem, like traveling salesperson, or packing boxes into the trunk of your car, or something like that. And I ask not just is there a solution, which would be an NP problem, but I ask how many solutions are there. Okay, that count the number of valid solutions. That actually gives those problems lie in a complexity class called sharp P, or it looks like hashtag P.
Got it.
Okay, which sits between NP and P space. There's all the problems that you can do in exponential time. Okay, that's called exp. So, and by the way, it was proven in the 60s that exp is larger than P. Okay, so we know that much. We know that there are problems that are solvable in exponential time that are not solvable in polynomial time. Okay. In fact, we even know more. We know that there are problems that are solvable in n cubed time that are not solvable in n squared time.
And those don't help us with a controversy between P and NP.
Unfortunately, it seems not, or certainly not yet. Right. The techniques that we use to establish those things, they're very, very related to how Turing proved the unsolvability of the halting problem, but they seem to break down when we're comparing two different resources, like time versus space, or P versus NP. Okay, but there's what you can do with a randomized algorithm, right? That can sometimes, has some probability of making a mistake. That's called BPP, bounded error probabilistic polynomial time.
Wow.
And then, of course, there's one that's very close to my own heart: what you can efficiently do in polynomial time using a quantum computer. Okay, and that's called BQP, right? And so,
what's understood about that class? Maybe as a comment.
So P is contained in BPP, which is contained in BQP, which is contained in P space. Okay, so anything you can, in fact, in something very similar to sharp P. BQP is basically, it's contained in P with the magic power to solve sharp P problems. Okay,
why is BQP contained in P space?
Oh, that's an excellent question. So there is one has to prove that, okay?
Right.
But the proof you could think of it as using Richard Feynman's picture of quantum mechanics, which is that you can always, we haven't really talked about quantum mechanics in this conversation. We did in our previous one.
We did last time.
But we did last time. Okay, but basically, you can always think of a quantum computation as a branching tree of possibilities, where each possible path that you could take through the space has a complex number attached to it called an amplitude. Okay, and now the rule is, when you make a measurement at the end, you see a random answer. Okay, but quantum mechanics is all about calculating the probability that you're going to see one potential answer versus another one, right? And the rule for calculating the probability that you'll see some answer is that you have to add up the amplitudes for all of the paths that could have led to that answer. And then, that's a complex number, so that, how could that be a probability? Then you take the squared absolute value of the result. That gives you a number between 0 and 1. Okay, so I just summarized quantum mechanics in 30 seconds. Okay, but now what this already tells us is that anything I can do with a quantum computer, I could simulate with a classical computer if I only have exponentially more time. Okay, and why is that? Because if I have exponential time, I could just write down this entire branching tree and just explicitly calculate each of these amplitudes. right? That will be very inefficient, but it will work, right? It's enough to show that quantum computers could not solve the halting problem, or, they could never do anything that is literally uncomputable in Turing's sense. Okay, but now, as I said, there's even a stronger result, which says that BQP is contained in P space. The way that we prove that is that we say, if all I want is to calculate the probability of some particular output happening, which is all I need to simulate a quantum computer, really, then I don't need to write down the entire quantum state, which is an exponentially large object. All I need to do is just calculate what is the amplitude for that final state. And to do that, I just have to sum up all the amplitudes that lead to that state. Okay, so that's an exponentially large sum, but I can calculate it just reusing the same memory over and over for each term in the sum.
Hence the P in the P space.
Hence the P space.
Yeah.
Yeah.
So what, out of that whole complexity zoo, it could be BQP, what do you find is the most, the class that captured your heart the most? Was the most beautiful class? It's just... Yeah,
I used as my email address bqpqpoly@gmail.com, just because bqp/qpoly. Amazingly, no one had taken it. Okay?
Amazing.
But this is a class that I was involved in, sort of proving the first theorems about in 2003 or so. So it was kind of close to my heart. But this is like if we extended BQP, which is the class of everything we can do efficiently with a quantum computer, to allow quantum advice, which means imagine that you had some special initial state, okay, that could somehow help you do computation. And maybe such a state would be exponentially hard to prepare, okay, but, maybe somehow these states were formed in the Big Bang or something, and they've just been sitting around ever since, right? If you found one, and if this state could be like ultra power, there are no limits on how powerful it could be, except that this state doesn't know in advance which input you've got, right? It only knows the size of your input. And then that's BQP/qpoly. So that's one that I just personally happen to love. Okay, but if you're asking like what's the there's a class that I think is way more beautiful than or fundamental than a lot of people even within this field realize that it is. That class is called SZK, or statistical zero knowledge. And there's a very, very easy way to define this class, which is to say, suppose that I have two algorithms that each sample from probability distributions, right? So each one just outputs random samples according to, possibly different distributions. And now the question I ask is, let's say distributions over strings of n bits, so over an exponentially large space. Now I ask, are these two distributions close or far as probability distributions? Okay, any problem that can be reduced to that, that can be put into that form, is an SZK problem. And the way that this class was originally discovered was completely different from that and was kind of more complicated. It was discovered as the class of all of the problems that have a certain kind of what's called zero knowledge proof. The zero knowledge proofs are one of the central ideas in cryptography. Shafi Goldwasser and Silvio Micali won the Turing Award for, inventing them. And they're at the core of even some cryptocurrencies that, people use nowadays. But their zero knowledge proofs are ways of proving to someone that something is true. Like, that there is a solution to this, optimization problem, or that these two graphs are isomorphic to each other or something, but without revealing why it's true, without revealing anything about why it's true. Okay. SZK is all of the problems for which there is such a proof that doesn't rely on any cryptography. Okay. And if you wonder, like, how could such a thing possibly exist, right? Well, like, imagine that I had two graphs and I wanted to convince you that these two graphs are not isomorphic, meaning, I cannot permute one of them so that it's the same as the other one, right? That might be a very hard statement to prove. Like I might need, you might have to do a very exhaustive enumeration of, all the different permutations before you were convinced that it was true. But what if there were some all-knowing wizard that said to you, look, I'll tell you what, just pick one of the graphs randomly, then randomly permute it, then send it to me, and I will tell you which graph you started with. Okay? And I will do that every single time. Right?
Let me load that in. Okay, that's I got it.
And let's say that wizard did that 100 times and it was right every time.
Yeah.
Right? Now, if the graphs were isomorphic, then it would have been flipping a coin each time. Yeah. Right? It would have had only a 1 in 2 to the 100 power chance of guessing right each time. But so if it's right every time, then now you're statistically convinced that these graphs are not isomorphic, even though you've learned nothing new about why they aren't.
So fascinating.
Right? So SDK is all of the problems that have protocols like that one, but it has this beautiful other characterization. It's shown up again and again in my own work, and a lot of people's work, and I think that it really is one of the most fundamental classes. It's just that people didn't realize that when it was first discovered.
I guess on a human level, what is the cost you're paying? What are you missing from not getting an updated picture all the time? Okay, I understand what you're just saying.
Yeah, right.
But how does consciousness emerge from that? Like how, what are the limitations of that observer? Okay. I understand you're getting a delayed picture.
there's a bunch of limitations of the observer, I think. Yeah. Maybe just explain something about quantum mechanics, because that maybe is an extreme version of some of these issues, which helps to kind of motivate why one should sort of think things through a little bit more carefully. So one feature of this, so in standard physics, like high school physics, you learn, the equations of motion for a ball, and it says you throw the ball this angle, this velocity, things will move in this way, and there's a definite answer. Right? The key story of quantum mechanics is there aren't definite answers to where does the ball go. There's kind of this whole sort of bundle of possible paths, and all we say we know from quantum mechanics is certain probabilities for where the ball will end up. Okay, so that's kind of the core idea of quantum mechanics. So in our models, quantum mechanics is not some kind of plug-in add-on type thing. You absolutely cannot get away from quantum mechanics, because as you think about updating this hypergraph, there isn't just one sequence of things, one definite sequence of things that can happen. There are all these different possible update sequences that can occur. You could do this, piece of the hypergraph now, and then this one later, and et cetera, et cetera, et cetera. All those different paths of history correspond to these quantum paths in quantum mechanics, these different possible quantum histories. And one of the things that's kind of surprising about it is they branch. There can be a certain state of the universe, and it could do this or it could do that, but they can also merge. There can be two states of the universe, which the next state they produce is the same for both of them. Yeah. And that process of branching and merging is kind of critical. And the idea that there can be merging is critical and somewhat non-trivial for these hypergraphs, because there's a whole graph isomorphism story, and there's a whole very elaborate set of mathematics.
That's where the causal invariance comes in.
Yes, among other things. Right. Okay. Yes, that's. But so then what happens is that what one's seeing. Okay, so we've got this thing, it's branching, it's merging, et cetera, et cetera, et cetera. Okay, so now the question is, how do we perceive that? Why don't we notice that the universe is branching and merging? Why is it the case that we just think a definite set of things happen? Well, the answer is we are embedded in that universe, and our brains are branching and merging too. And so what quantum mechanics becomes a story of is, how does a branching brain perceive a branching universe? And the key thing is, as soon as you say, I think definite things happen in the universe, that means you are essentially conflating lots of different paths of history. You're saying, actually, as far as I'm concerned, because I'm convinced that definite things happen in the universe, all these paths of history must be equivalent. Now, it's not obvious that that would be a consistent thing to do. It might be you say all these paths of history are equivalent, but by golly, moments later, that would be a completely inconsistent point of view. Everything would have, gone to hell in different ways. The fact that that doesn't happen is, well, that's a consequence of this causal invariance thing, but and the fact that that does happen a little bit is what causes little quantum effects. And that if that didn't happen at all, there wouldn't be anything that sort of is like quantum mechanics. It would be, quantum mechanics is kind of like in this kind of this bundle of paths. It's a little bit like what happens in statistical mechanics and fluid mechanics, whatever, that most of the time you just see this continuous fluid. You just see the world just progressing in this kind of way that's like this continuous fluid. But every so often, if you look at the exact right experiment, you can start seeing, well, actually, it's made of these molecules where they might go that way or they might go this way. And that's kind of quantum effects. And so this kind of idea of where we're sort of embedded in the universe, this branching brain is perceiving this branching universe, and that ends up being sort of a story of quantum mechanics. That's part of the whole picture of what's going on. But I mean, to come back to sort of what is the story of consciousness? So in the universe, we've got, whatever it is, 10 to the 400 atoms of space. They're all doing these complicated things. It's all a big, complicated, irreducible computation. The question is, what do we perceive from all of that? And the answer is that we are parsing the universe in a particular way. Let me again go back to the gas molecules analogy. In the gas in this room, there are molecules bouncing around in all kinds of complicated patterns, but we don't care. All we notice is there's, the gas laws are satisfied. Maybe there's some fluid dynamics. These are kind of features of that assembly of molecules that we notice, and then lots of details we don't notice.
When you say we, do you mean the tools of physics, or do you mean literally the human brain and its perception system?
Well, okay, so the human brain is where it starts, but we've built a bunch of instruments to do a bit better than the human brain, but they still have many of the same kinds of ideas, their cameras and their pressure sensors and their these kinds of things. They're not, at this point, we don't know how to make fundamentally qualitatively different sensory devices.
Right. And so it's always just an extension of the conscious experience.
Or our sensory experience.
Sensory experience, but sensory experience that's somehow intricately tied to consciousness.
Right. Well, so one question is, when we are looking at all these molecules in the gas, and there might be 10 to the 20th molecules in some little box or something, it's like, what do we notice about those molecules? So one thing that we can say is we don't notice that much. We are computationally bounded observers. We can't go in and say, okay, they're 10 to the 20th molecules, and I know that I can sort of decrypt their motions and I can figure out this and that. It's like, I'm just going to say what's the average density of molecules. And so one key feature of us is that we are computationally bounded. And that when you are looking at a universe which is full of computation and doing huge amounts of computation, but we are computationally bounded, there's only certain things about that universe that we're going to be sensitive to. We're not going to be, figuring out what all the atoms of space are doing, because we're just computationally bounded observers, and we are only sampling these small set of features. So I think the two defining features of consciousness I would say that the sort of the preamble to this is, for years, because I've talked about sort of computation and fundamental features of physics and science, people ask me, so what about consciousness? And for years, I've said, I have nothing to say about consciousness. And, I've kind of told this story, you talk about intelligence, you talk about life. These are both features where you say, what's the abstract definition of life? We don't really know the abstract definition. We know the one for life on Earth. It's got RNA, it's got cell membranes, it's got all this kind of stuff. Similarly, for intelligence, we know the human definition of intelligence, but what is intelligence abstractly? We don't really know. And so what I've long believed is that sort of the abstract definition of intelligence is just computational sophistication. That is, that as soon as you can be computationally sophisticated, that's kind of the abstract version, the generalized version of intelligence. So then the question is, what about consciousness? And what I sort of realized is that consciousness is actually a step down from intelligence. That is, that you might think, consciousness is the top of the pile. But actually, I don't think it is. I think that there's this notion of kind of computational sophistication, which is the generalized intelligence. But consciousness has two limitations, I think. One of them is computational boundedness. That is, that we're only perceiving a sort of computationally bounded view of the universe. And the other is this idea of a single thread of time. That is, that and in fact, we know neurophysiologically our brains go to some trouble to give us this one thread of attention, so to speak. And it isn't the case that, in all the neurons in our brains that in at least in our conscious, the correspondence of language, in our conscious experience, we just have this single thread of attention, single thread of perception. And maybe there's something unconscious that's bubbling around. That's the kind of almost the quantum version of what's happening in our brain, so to speak. We've got the classical flow of what we are mostly thinking about, so to speak. But there's this kind of bubbling around of other paths that is all those other neurons that didn't make it to be part of our sort of conscious stream of experience.
Do you see this world where just everything's a computing surface? You see that possibility? Just everything's a computer?
Yeah, I don't see any reason that couldn't be achieved. It turns out that sand goes into glass, and glass is pretty useful too. And, why not?
Why not? So, right. The very important question then, if we're living in a simulation and the simulation is running a computer, like what's the architecture of that computer, do you think?
So you're saying, is it a quantum system? Is it
like this whole quantum discussion, is it needed, or can we run it on a with a RISC-V architecture, a bunch of CPUs?
I think it comes down to the right tool for the job. Okay, and
what's the compiler?
Yeah, exactly. That's my question. How do I get that job? Be the universe compiler. And so there, as far as we know, quantum systems are the bottom of the pile of turtles so far.
Yeah.
And so we don't know efficient ways to implement quantum systems without using quantum computers.
Yeah, and that's totally outside of everything we've talked about.
But who runs that quantum computer?
Yeah.
Right. So if we really are living in a simulation, then is it bigger quantum computers? Is it different ones? Like, how does that work out? How does that scale?
Well, it's the same size. It's the same size. But then the thought of the simulation is that you don't have to run the whole thing. That we humans are cognitively very limited.
Do checkpoints.
Checkpoints, yeah. And if the point at which we so you basically do minimal amount of what is it? The Swift does on write. Copy on write,
yeah.
So you only adjust the simulation every
parallel universe theories, right? And so every time a decision's made, somebody opens the Schrodinger box, then there's a fork, right? And then this could happen.
And then thank you for for considering the possibility. But yeah, so it may not require the entirety of the universe to simulate it, but it's interesting to think about. As we create this higher and higher fidelity systems, but I do want to ask on the quantum computer side, because everything we've talked about with you work with sci-fi, with compilers, none of that includes quantum computers, right?
That's true.
So, have you ever thought about this whole serious engineering work of quantum computers looks like, of compilers, of architectures, all of that kind of stuff?
So I've looked at it a little bit. I know almost nothing about it, which means that at some point I will have to find an excuse to get involved, because that's how. But
do you think that's a thing to be like? With your little tingly senses of the timing of when to be involved? Is it not yet?
Well, so the thing I do really well is I jump into messy systems and figure out how to make them, figure out what the truth in the situation is, try to figure out what the unifying theory is, how to factor the complexity, how to find a beautiful answer to a problem that has been well studied and lots of people have bashed their heads against it. I don't know that quantum computers are mature enough and accessible enough to be figured out yet, right? And I think the open question with quantum computers is there a useful problem that gets solved with a quantum computer that makes it worth the economic cost of having one of these things and having legions of people that set it up. You go back to the 50s, right? And there's the projections of the world will only need seven computers, right?
Yeah.
Well, and part of that was that people hadn't figured out what they're useful for. Yeah. What are the algorithms we want to run? What are the problems that get solved? And this comes back to, how do we make the world better either economically or making somebody's life better or like solving a problem that wasn't solved before, things like this. And I think that just we're a little bit too early in that development cycle because it's still like literally a science project, not in a negative connotation, right? It's literally a science project, and the progress there is amazing. And so I don't know if it's 10 years away, if it's 2 years away, exactly where that breakthrough happens. But you look at machine learning, we went through a few winners before the AlexNet transition, and then suddenly it had its breakout moment, and that was the catalyst that then drove the talent flocking into it. That's what drove the economic applications of it. That's what drove the technology to go faster because you now have more minds thrown at the problem. This is what caused a serious knee in deep learning and the algorithms that we're using. And so I think that's what quantum needs to go through. And so right now it's in that formidable finding itself, getting the literally the physics figured out, and then
it has to figure out the application that makes that's useful. Like
but I'm not skeptical that I think that will happen. I think it's just 10 years away, something like that.
I forgot to ask, what programming language do you think the simulation is written in?
Ooh, probably Lisp.
So not Swift. Like if you were to bet,
So
that's really interesting.
Yeah.
So on another architecture type, I mean, you mentioned Schrödinger's equation, and what are your thoughts about quantum computing and the role of this kind of computational unit in creating an intelligent system?
in some Hollywood movies that I will not mention by name because I don't want to spoil them, the way they get AGI is building a quantum computer. Because the word quantum sounds cool and so on.
That's right.
First of all, I think we don't need quantum computers to build AGI. I suspect your brain is not a quantum computer in any profound sense.
So you don't
I even wrote a paper about that many years ago. I calculated the decoherence, so-called decoherence time, that how long it takes until the quantum computerness of what your neurons are doing gets erased by just random noise from the environment, and it's about 10 to the minus 21 seconds. So as cool as it would be to have a quantum computer in my head, I don't think that fast.
Yeah.
On the other hand, there are very cool things you could do with quantum computers, or I think we'll be able to do soon when we get bigger ones, that might actually help machine learning do even better than the brain.
Mm-hmm.
So, for example, this is just a moonshot, but the learning is very much the same thing as search.
Mm-hmm.
If you're trying to train a neural network to learn to do something really well, you have some loss function, you have a bunch of knobs you can turn, represented by a bunch of numbers, and you're trying to tweak them so that it becomes as good as possible at this thing. So if you think of a landscape with some valley, where each dimension of the landscape corresponds to some number you can change, you're trying to find the minimum. And it's well known that if you have a very high dimensional landscape, complicated things, it's super hard to find the minimum, right? Quantum mechanics is amazingly good at this.
Right.
Like if I want to know what's the lowest energy state this water can possibly have, incredibly hard to compute, but we can. But nature will happily figure this out for you if you just cool it down, make it very, very cold. If you put a ball somewhere, it'll roll down to its minimum, and this happens metaphorically at the energy landscape too. And quantum mechanics even uses some clever tricks, which today's machine learning systems don't. Like if you're trying to find the minimum and you get stuck in a little local minimum here, in quantum mechanics you can actually tunnel through the barrier and get unstuck again. And
that's really interesting.
Yeah, so maybe, for example, we'll one day use quantum computers to help train neural networks better.
That's a story which, in a sense, I haven't finished.
Yes.
Because I went to these 3 courses, you see, when I was a graduate student. And so I started to think, well, I'm a pretty, what you might call a materialist in the sense of thinking that there's no kind of mystical something or other which comes in from who knows where.
You still that? Are you still throughout your life been a
I don't like the word materialist because it suggests we know what material is. And that is a bad word because
but there's no mystical.
It's not some mystical something which is not treatable by science.
That's so beautifully put. Just to pause on that for a second. You're a materialist, but you acknowledge that we don't really know what the material is.
That's right. I mean, I like to call myself a scientist, I suppose, but it means that, yes, well, you see, the question goes on here. So I began thinking, okay, if consciousness or understanding is something which is not a computational process, what can it be? And I knew enough from my undergraduate work. I knew about Newtonian mechanics, and I knew how basically you could put it on a computer. There is a fundamental issue, which is it important or not, that computation depends upon discrete things, so you're using discrete elements, whereas the physical laws depend on the continuum. Now, is this something to do with it? Is it the fact that we use the continuum in our physics, and if we model our physical system, we use discrete systems like ordinary computers? I came to the view that that's probably not it. I might have to retract on that someday, but the view was no, you can get close enough. It's not altogether clear, I have to say, but you can get close enough. And, I went to this course by Bondi on general relativity, and I thought, well, you can put that on a computer. Of course, that was a long time before people... I've sort of grown up with this, how people have done better and better calculations, and they could work out about black holes, and they can then work out how black holes can interact with each other, spiral around, and what kind of gravitational waves come out. And it's a very impressive piece of computational work, how you can actually work out the shapes of those signals. And now we have LIGO seeing these signals, and they say, yeah, those black holes spiral into each other. This is just a vindication of the power of computation in describing Einstein's general relativity.
So in that case, we can get close. But so with computation, we can get close to our understanding of the physics.
You can get very, very close. Now, is that close enough, you see? And then I went to this course by Dirac. Now, you see, I think it was the very first lecture that he gave. And he was talking about the superposition principle. And he said, if you have a particle, you usually think of particle can be over here or over there, but in quantum mechanics, it can be over here and over there at the same time. And you have these states which involve a superposition, in some sense, of different locations for that particle. And then he got out his piece of chalk. Some people say he broke it in two as a kind of illustration of how the piece of chalk might be over here and over there at the same time. And he was talking about this, and my mind wandered. I don't remember what he said. All I can remember, he just moved on to the next topic, and something about energy he'd mentioned, which I had no idea what it had to do with anything. And so I'd been struck with this and worried about it ever since. It's probably just as well I didn't hear his explanation, because it was probably one of these things to calm me down and not worry about it anymore. Whereas in my case, I've worried about it ever since. So I thought, maybe that's the catch. There is something in quantum mechanics where these superpositions become one or the other. And that's not part of quantum mechanics. There's something missing in the theory. The theory is incomplete. It's not just incomplete, it's in a certain sense not quite right. Because if you follow the equation, the basic equation of quantum mechanics, that's the Schrödinger equation, you could put that on a computer too. There are lots of difficulties about how many parameters you have to put in and so on. That can be very tricky, but nevertheless, it is a computational process. Modulo this question about the continuum as before, but it's not clear that makes any difference.
So our theories of quantum mechanics may be missing the same element that the universal Turing machine is missing about consciousness.
Yes. Yeah, this is the view I held, is that you need a theory, and that what people call the reduction of the state or the collapse of the wave function, which you have to have, otherwise quantum mechanics doesn't relate to the world we see. To make it relate to the world we see, you've got to break the Schrödinger equation. Schrödinger himself was absolutely appalled by this idea, his own equation. I mean, that's why he introduced this famous Schrodinger's cat as a thought experiment. He's really saying, look, this is where my equation leads you into it. There's something wrong, something we haven't understood, which is basically fundamental. And so I was trying to put all these things together and said, well, it's got to be the non-computability comes in there. And I also can't quite remember when I thought this, but it's when gravity is involved in quantum mechanics. It's the combination of those two, and it's that point when you have good reasons to believe, this came much later, but I have good reason to believe that the principles of general relativity and those of quantum mechanics, most particularly, it's the basic principle of equivalence, which goes back to Galileo. If you fall freely, you eliminate the gravitational field. So you imagine Galileo dropping his big rock and his little rock from the Leaning Tower, whether he actually ever did that or not, it's pretty irrelevant. And as the rocks fall to the ground, you have a little insect sitting on one of them looking at the other one. And it seems to think, oh, there's no gravity here. Of course, it hits the ground and then it realizes something different's going on. But when it's in free fall, the gravity has been eliminated. Galileo understood that very beautifully. He gives these wonderful examples of fireworks. And you see the fireworks and explode, and you see the sphere of sparkling fireworks. It remains a sphere as it falls down, as though there were no gravity. So he understood that principle, but he couldn't make a theory out of it. Einstein came along, used exactly the same principle, and that's the basis of Einstein's general theory of relativity. Now, there is a conflict. This is something I did much, much later, so this wasn't those days. Much, much later. You can see there is a basic conflict between the principle of superposition, the thing that Dirac was talking about, and the principle of general covariance. Well, principle of equivalence. Gravitational field is equivalent to an acceleration.
Can you pause for a second? What is the principle of equivalence?
It's this Galileo principle that you can eliminate, at least locally. You have to be in a small neighborhood, because if you have people dropping rocks all around the world somewhere, you can't get rid of it all at once. But in the local neighborhood, you can eliminate the gravitational field by falling freely with it. And we now see that with astronauts, and they don't, the Earth is right there. You can see the great globe of the Earth right beneath them. But they don't care about it. As far as they're concerned, there's no gravity. Mm-hmm. They fall freely in the gravitational field, and that gets rid of the gravitational field. And that's the principle of equivalence.
So what's the contradiction? What's the tension with superposition and the
that's
equivalence?
Technical.
Well, but so just to backtrack for a second, just to see if we can weave a thread through it all.
Yes.
So we started to think about consciousness as potentially needing some of the same, not mystical, but some of the same magic. Your most recent book, titled Einstein's Unfinished Revolution. So I have to ask, what is Einstein's Unfinished Revolution? And also, how do we finish it?
Well, that's something I've been trying to do my whole life. But Einstein's Unfinished Revolution is the twin revolutions which invented relativity theory, special and especially general relativity, and quantum theory, which he was the first person to realize in 1905 that there would have to be a radically different theory which somehow realized or resolved the paradox of the duality of particle and wave for photons.
And he was, people, I think, don't always associate Einstein with quantum mechanics, because I think his connection with it, founding as one of the founders, I would say, of quantum mechanics, he kind of put it in the closet.
Well, he didn't believe that the quantum mechanics, as it was developed in the mid-late 1920s, was completely correct. At first, he didn't believe it at all. Then he was convinced that it's consistent but incomplete, and that also is my view. It needs, for various reasons I can elucidate, to have additional degrees of freedom, particles, forces, something to reach the stage where it gives a complete description of each phenomenon, as I was saying, realism demands.
So what aspect of quantum mechanics bothers you and Einstein the most? Is it some aspect of the wave function collapse discussions, the measurement problem? Is it the
measurement problem? I'm not going to speak for Einstein, but the measurement problem, basically, and the fact that
what is the measurement problem? Sorry.
The basic formulation of quantum mechanics gives you two ways to evolve situations in time. One of them is explicitly when no observer is observing or no measurement is taking place. And the other is when a measurement or an observation is taking place. And they basically contradict each other. But there's another reason why the revolution was incomplete, which is we don't understand the relationship between these two parts. General relativity, which became our best theory of space and time and gravitation and cosmology, and quantum theory.
So for the most part, general relativity describes big things, quantum theory describes little things, and that's the revolution that we found really powerful tools to describe big things and little things, and it's unfinished because we have two totally separate things, and we need to figure out how to connect them so it can describe everything.
Right, and we either do that, if we believe quantum mechanics as understood now is correct, by bringing general relativity or some extension of general relativity that describes gravity and so forth into the quantum domain. That's called quantize, the theory of gravity. Or if you believe with Einstein that quantum mechanics needs to be completed, and this is my view, then part of the job of finding the right completion or extension of quantum mechanics would be one that incorporated space-time and gravity.
So, where do we begin? So, first, let me ask, perhaps you can give me a chance, if I could ask you some just really basic questions. Well, they're not at all. The basic questions are the hardest, but you mentioned space-time. What is space-time?
Space-time, you talked about a construction. So I believe that space-time is an intellectual construction that we make of the events in the universe. I believe the events are real, and the relationships between the events, which cause which, are real. But the idea that there's a four-dimensional smooth geometry which has a metric and a connection and satisfies the equations that Einstein wrote, it's a good description to some scale. It's a good approximation. It captures some of what's really going on in nature. But I don't believe it for a minute is fundamental.
So, okay, we're going to allow me to linger on that. So the universe has events.
Yeah.
Events cause other events.
Yeah.
This is the idea of causality. Okay, yeah. So that's real.
That's in my...
In your view, is real.
Or hypothesis, or the theories that I have been working to develop make that assumption.
Yes. So space-time, you said four-dimensional. Space is kind of the location of things, and time is whatever the heck time is. And you're saying that space-time is both space and time are emergent and not fundamental?
No.
First, sorry, before you correct me, what does it mean to be fundamental or emergent?
Fundamental means it's part of the description as far down as you go. We have this
real.
notion. Yes.
As real it could be.
Yeah. So I think that time is fundamental and quote goes all the way down, and space does not.
Right.
And the combination of them we use in general relativity that we call space-time also does not.
But what is time then?
I think that time, the activity of time, is the continual creation of events from existing events.
So if there's no events, there's no
nothing.
Time.
Then there's not only no time, there's no nothing.
So
I believe the universe has a history which goes to the past. I believe the future does not exist. There's a notion of a present and a notion of the past. And the past is a story about events that took place to our past.
So you said the future doesn't exist.
Yes.
Could you say that again? Can you try to give me a chance to understand that one more time? So, what the events cause other events? What is this universe? Because we'll talk about locality and non-locality.
Good.
Because it's a crazy. I mean, it's not crazy. It's a beautiful set of ideas that you propose. But and if causality is fundamental, I just like to understand it better. What is the past? What is the future? What is the flow of time, even the error of time in our universe, in your view? And maybe what's an event, right?
Oh, an event is where something changes, or where it's hard to say because it's a primitive concept. And an event is a moment of time within space. This is the view in general relativity, where two particles intersect in their paths, or something changes in the path of a particle. Now, we are postulating that there is, at the fundamental level, a notion, which is an elementary notion, so it doesn't have a definition in terms of other things, but it is something elementary happening.
And it doesn't have a connection to energy or matter or exchange of any.
It does have a connection to energy and matter.
So it's at that level.
Yes, it involves, and that's why the version of a theory of events that I've developed with Marina Cortez. And it's, by the way, I want to mention my collaborators because they've been at least as important in this work as I have. There's Marina Cortez in all the work since about 2013, 2012, 2013 about causality, causal sets. And in the period before that, Roberto Manguibera-Unger, who is a philosopher and a professor of law.
And that's in your efforts together with your collaborators to finish the unfinished revolution. So,
yes.
And focused on causality as a fundamental,
yes,
as fundamental to physics. So,
and there's certainly other people we've worked with, but those two people's thinking had a huge influence on my own thinking.
So, in the way you describe causality, that's what you mean of time being fundamental. That causality is fundamental.
Yes.
And what does it mean for space to not be fundamental, to be emergent?
That's very good. There's a level of description in which there are events create other events, but there's no space. They don't live in space. They have an order in which they caused each other. And that is part of the nature of time for us. So, but there is an emergent approximate description, and you asked me to define emergent, I didn't. An emergent property is a property that arises at some level of complexity larger than and more complex than the fundamental level, which requires some property to describe it, which is not directly explicable or derivable is the word I want, from the properties of the fundamental things.
And space is one of those things in a sufficiently complex universe. Space, three-dimensional position of things emerged.
Yes, and we saw how this happens in detail in some models, both computationally and analytically.
Okay, so connected to space is the idea of locality.
Yes.
So we talked about realism. So I live in this world that, like sports, locality is a thing that, you can affect things close to you and don't have an effect on things that are far away.
Mm-hmm.
It's the thing that bothers me about gravity in general, or action at a distance. Mm-hmm. Same thing that probably bothered Newton, or at least he said a little bit about it. Okay, so what do you think about locality? Is it just a construct? Is it us humans just like this idea and are connected to it because we exist in it, we need it for our survival, but it's not fundamental? I mean, it seems crazy for it not to be a fundamental aspect of our reality.
It does.
And so can you comfort me on a sort of as a therapist? Like, how do I?
I'm not a good therapist, but I'll do my best.
Okay.
There are several different definitions of locality when you come to talk about locality in physics. In quantum field theory, which is a mixture of special relativity and quantum mechanics, there is a precise definition of locality. Field operators corresponding to events in space-time which are space-like separated commute with each other as operators.
So in quantum mechanics, you think about the nature of reality as fields, and things that are close in a field have an impact on each other more than farther away.
Yes.
That's very comforting. That makes sense.
So that's a property of quantum field theory, and it's well tested. Unfortunately, there's another definition of local, which was expressed by Einstein and expressed more precisely by John Bell, which has been tested experimentally and found to fail. And this setup is you take two particles. So one thing that's really weird about quantum mechanics is a property called entanglement. Mm-hmm. You can have two particles interact and then share a property without it being a property of either one of the two particles. And if you take such a system and then you make a measurement on particle A, which is over here on my right side, and particle B, which is over here, and somebody else makes a measurement of particle B, you can ask that whatever is the real reality of particle B, it not be affected by the choice the observer at particle A makes about what to measure, not the outcome, just the choice of the different things they might measure. And that's a notion of locality because it assumes that these things are very far space-like separated, and it's going to take a while for any information about the choice made by the people here at A to affect the reality at B. But you make that assumption, that's called Bell locality. Mm-hmm. And you derive a certain inequality that some correlations, functions of correlations have to satisfy. And then you can test that pretty directly in experiments which create pairs of photons or other particles. And it's wrong by many sigma.
In experiment, it doesn't match. So what does that mean?
That means that definition of locality I stated is false.
The one that Einstein was playing with.
Yeah, and the one that I stated, that is, it's not true that whatever is real about particle B is unaffected by the choice that the observer makes as to what to measure in particle A, no matter how long they've been propagating at almost the speed of light or the speed of light away from each other.
No matter? So like the distance between them?
Well, it's been tested, of course. If you want to have hope for quantum mechanics being incomplete or wrong and corrected by something that changes this, it's been tested over a number of kilometers. I don't remember whether it's 25 kilometers or 100 and something kilometers. But
so in trying to solve the unsolved revolution, in trying to come up with a theory for everything, is causality fundamental and breaking away from locality?
Absolutely.
A crucial step. Yeah. So in your book, essentially, those are the two things we really need to think about as a community. So especially the physics community has to think about this. So I guess my question is, how do we finish the unfinished revolution?
Well, I can only tell you what I'm trying to do and what I have abandoned.
Yes,
exactly. As not working.
As one smart ant in an ant colony. Yep.
Or maybe dumb, that's why. Who knows? But anyway, my view we've had some nice theories invented. Yes. There's a bunch of different ones, both related to quantum mechanics and related to quantum gravity. There's a lot to admire in many of these different approaches, but to my understanding, none of them completely solve the problems that I care about. And so we're in a situation which is either terrifying for a student or full of opportunity for the right student, in which we've got more than a dozen attempts. And I don't think anybody anticipated it would work out this way, which work partly, and then at some point they have an issue that nobody can figure out how to go around or how to solve. And that's the situation we're in. My reaction to that is twofold. One of them is to try to bring people. We evolved into this unfortunate sociological situation in which there are communities around some of these approaches. And to borrow again a metaphor from Eric, they sit on top of hills in the landscape of theories and throw rocks at each other. And as Eric says, we need two things. We need people to get off their hills and come down into the valleys and party and talk and become friendly and learn to say not no but yes and. Yes, your idea goes this far, but maybe if we put it together with my idea, we can go further.
Yes. So in that spirit, I've talked several times with Sean Carroll, who's also written an excellent book recently, and he plays around, is a big fan of the many worlds interpretation of quantum mechanics. So I'm a troublemaker. So let me ask, what's your sense of Sean and the idea of many worlds interpretation? I've read the commentary back and forth. You guys are friendly, respect each other, but have a lot of fun debating.
I love Sean, and he's articulate, and he's a great representative or ambassador of science to the public and for different fields of science to each other. He also, like I do, takes philosophy seriously. And unlike what I do in all cases, he has really done the homework. He's read a lot. He knows the people. He talks to them. He exposes his arguments to them. And there's this mysterious thing that we so often end up on the opposite sides of with these issues.
It's fun, though.
It's fun, and I'd love to have a conversation about that, but I would want to include him.
I see. About many worlds. Well,
no, I can tell you what I think about many worlds.
I'd love to, but actually on that, let me pause. Sean has a podcast. You should definitely figure out how to talk to Sean. I actually told Sean I would love to hear you guys just going back and forth. So I hope you can make that happen eventually, you and Sean.
I won't tell you what it is, but there's something that Sean said to me in June of 2016 that changed my whole approach to a problem. But I have to tell him first.
Yes, and that'll be great to tell him on his podcast. So
I can't invite myself to his podcast.
I told him, yeah, okay, we'll make it happen. So many worlds.
Anyway,
what's your view? Many worlds. We talk about non-locality. Many worlds is also a very uncomfortable idea, or beautiful, depending on your perspective. It's very nice in terms of. I mean, there's a realist aspect to it. I think you called it magical realism.
Yeah.
Just a beautiful line. But at the same time, it's very difficult for our limited human minds to comprehend. So what are your thoughts about it?
Let me start with the easy and obvious and then go to the scientific.
Okay.
It doesn't appeal to me. It doesn't answer the questions that I want answered. And it does so to such a strong case that when Roberto Manguiber-Unger and I began looking for principles, and I want to come back and talk about the use of principles in science, because that's the other thing I was going to say, and I don't want to lose that. When we started looking for principles, we made our first principle, there is just one world, and it happens once. But, so it's not helpful to my personal approach, to my personal agenda. But of course, I'm part of a community. And my sense of the many worlds interpretation, I have thought a lot about it and struggled a lot with it, is the following. first of all, there's Everett himself. There's what's in Everett. And there are several issues there connected with the derivation of the Born rule, which is the rule that gives probabilities to events. And the reasons why there is a problem with probability is that I mentioned the two ways that physical systems can evolve. The many worlds interpretation cuts off the one having to do with measurement, and just has the other one, the Schrodinger evolution, which is the smooth evolution of the quantum state. But the notion of probability is only in the second rule, which we've thrown away. So where does probability come from? And you have to answer the question, because experimentalists use probabilities to check the theory. Now, at first sight, you get very confused because there seems to be a real problem, because in the many worlds interpretation, this talk about branches is not quite precise, but I'll use it. There's a branch in which everything that might happen does happen, with probability 1 in that branch. You might think you could count the number of branches in which things do and don't happen, and get numbers that you can define as something like frequentist probabilities. And Everett did have an argument in that direction, but the argument gets very subtle when there are an infinite number of possibilities, as is the case in most quantum systems. And my understanding, although I'm not as much of an expert as some other people, is that Everett's own proposal failed, did not work. There are then, but it doesn't stop there. There is an important idea that Everett didn't know about, which is decoherence, and it is a phenomenon that might be very much relevant. And so a number of people post-Everett have tried to make versions of what you might call many worlds quantum mechanics. And this is a big area, and it's subtle, and it's not the kind of thing that I do well. So I consulted. That's why there's 2 chapters on this in the book I wrote. Chapter 10, which is about Everett's version, and Chapter 11. There's a very good group of philosophers of physics in Oxford. Simon Saunders, David Wallace, Harvey Brown, and a number of others. And of course, there's David Deutsch, who is there. And those people have developed and put a lot of work into a very sophisticated set of ideas designed to come back and answer that question. They have the flavor of, there are really no probabilities, we admit that. But imagine if the Everett story was true and you were living in that multiverse, how would you make bets? And so they use decision theory from the theory of probability and gambling and so forth to shape a story of how you would bet if you were inside an Everettian universe and you knew that. And there's a debate among those experts as to whether they or somebody else has really succeeded. And when I checked in as I was finishing the book with some of those people, like Simon, who's a good friend of mine, and David Wallace, they told me that they weren't sure that any of them was yet correct. So that's what I put in my book. Now, to add to that, Sean has his own approach to that problem in what's called self-referencing or self-locating observers. And it doesn't, I tried to read it and it didn't make sense to me, but I didn't study it hard. I didn't communicate with Sean. I didn't do the things that I would do. So I had nothing to say about it in the book. Yeah. I don't know whether it's right or not.
What are your hopes for quantum computers? So machines that are based on, that have some elements of leverage quantum mechanical ideas.
Yeah. It's not just leveraging quantum mechanical ideas. You can simulate quantum systems on a classical computer. Simulate them means solve the Schrodinger equation for them, or solve the equations of quantum mechanics on a computer, on a classical computer. But the classical computer is not a quantum mechanical system itself. Oh, of course it is. Everything's made of quantum mechanics, but it's not functioning. Level. It's not functioning as a quantum system. It's just solving equations. The quantum computer is truly a quantum system which is actually doing the things that you're programming it to do. You want to program a quantum field theory? If you do it in classical physics, that program is not actually functioning in the computer as a quantum field theory. It's just solving some equations. Physically, it's not doing the things that the quantum system would do. The quantum computer is really a quantum mechanical system which is actually carrying out the quantum operations. You can measure it at the end. It intrinsically satisfies the uncertainty principle. It is limited in the same way that quantum systems are limited by uncertainty and so forth. And it really is a quantum system. That means that what you're doing when you program something for a quantum system is you're actually building a real version of the system. The limits of a classical computers are enormously limited when it comes to quantum systems. They're enormously limited because you probably heard this before, but in order to store the amount of information that's in a quantum state of 400 spins, that's not very many. 400 I can put in my pocket. I can put 400 pennies in my pocket. To be able to simulate the quantum state of 400 elementary quantum systems, qubits we call them, to do that would take more information than can possibly be stored in the entire universe if it were packed so tightly that you couldn't pack any more in.
Right.
400 qubits. On the other hand, if your quantum computer is composed of 400 qubits, it can do everything 400 qubits can do.
What kind of space, if you just intuitively think about the space of algorithms that unlocks for us? So there's a whole complexity theory around classical computers measuring the running time of things, NP, so on. What kind of algorithms, just intuitively, do you think it unlocks for us?
Okay, so we know that there are a handful of algorithms that can seriously beat classical computers and which can have exponentially more power.
Yeah.
This is a mathematical statement. Nobody's exhibited this in the laboratory. It's a mathematical statement. We know that's true, but it also seems more and more that the number of such things is very limited. Only very, very special problems exhibit that much advantage for a quantum computer of standard problems. To my mind, as far as I can tell, the great power of quantum computers will actually be to simulate quantum systems. If you're interested in a certain quantum system and it's too hard to simulate classically, you simply build a version of the same system. You build a version of it, you build a model of it that's actually functioning as the system, you run it, and then you do the same thing you would do to the quantum system, you make measurements on it, quantum measurements on it. The advantage is you can run it much slower. You could say, why bother? Why not just use the real system?
Right.
Why not just do experiments on the real system? Well, real systems are kind of limited. You can't change them. You can't manipulate them. You can't slow them down so that you can poke into them. You can't modify them in arbitrary kinds of ways to see what would happen if I change the system a little bit. So I think that quantum computers will be extremely valuable in understanding quantum systems.
At the lowest level, the fundamental laws.
Yeah, they're actually satisfying the same laws as the systems that they're simulating.
That's right.
Okay, so on the one hand, you have things like factoring.
Right.
Okay, factoring is the great thing of quantum computers, factoring large numbers. That doesn't seem to have much to do with quantum mechanics.
Right.
It seems to be almost a fluke that a quantum computer can solve the factoring problem in a short time. So those problems seem to be extremely special, rare, and it's not clear to me that there's going to be a lot of them. On the other hand, there are a lot of quantum systems. There's chemistry, there's solid state physics, there's material science, there's quantum gravity, there's all kinds of quantum field theory. And some of these are actually turning out to be applied sciences as well as very fundamental sciences. So we probably will run out of the ability to solve equations for these things. Solve equations by the standard methods of pencil and paper, solve the equations by the method of classical computers.
Mm-hmm.
And so what we'll do is we'll build versions of these systems, run them under controlled circumstances where we can change them, manipulate them, make measurements on them, and find out all the things we want to know.
So in finding out the things we want to know about very small systems, right?
Yeah.
Is there something we can also find out about the macro level, about something about the function, forgive me, of our brain, biological systems, the stuff that's about 1 meter in size versus much, much smaller?
Well, what all the excitement is about among the people that I interact with is understanding black holes.
Black holes.
Black holes are big things. They are many, many degrees of freedom. There is another kind of quantum system that is big. It's a large quantum computer. And one of the things we've learned is that the physics of large quantum computers is in some ways similar to the physics of large quantum black holes. And we're using that relationship. Now, you didn't ask about quantum computers as systems. You didn't ask about black holes. You asked about brains.
Yeah, about stuff that's in the middle of the two.
It's different.
So black holes are, there's something fundamental about black holes that feels to be very different than brains.
Yes. And they also function in a very quantum mechanical way.
Right.
Okay. It is, first of all, unclear to me, but of course it's unclear to me. I'm not a neuroscientist. I don't even have very many friends who are neuroscientists. I would like to have more friends who are neuroscientists. I just don't run into them very often. Among the few neuroscientists I've ever talked about this, they are pretty convinced that the brain functions classically, that it is not intrinsically a quantum mechanical system, or it doesn't make use of the special features, entanglement, coherent superposition. Are they right? I don't know. I sort of hope they're wrong, just because I like the romantic idea that the brain is a quantum system.
Yeah.
But I think probably not. The other thing, big systems can be composed of lots of little systems. Okay, materials, the materials that we work with and so forth can be large systems, a large piece of material, but they're big and they're made out of quantum systems. Now, one of the things that's been happening over the last a good number of years is we're discovering materials and quantum systems which function much more quantum mechanically than we imagine. Topological insulators, this kind of thing, that kind of thing. Those are macroscopic systems, but they just superconductors. Superconductors have a lot of quantum mechanics in them. You can have a large chunk of superconductor, so it's a big piece of material. On the other hand, its functioning and its properties depend very, very strongly on quantum mechanics. And to analyze them, you need the tools of quantum mechanics.